Do you understand what I'm saying? That's what we are doing. So this is being recorded, right?
Yeah, it's being recorded.
I can't, this one is having troubles. I can send it to you to whom? What you want.
So the thing is, the screen share is there.
Can we make a new meeting link? If Lynn is only joining, we can just give him the.
No, I understand, but what happened now?
So nothing. So we want, yeah, the host disabled participant.
Oh, this is not, whose host is it then?
So this is, you are the host, but I have logged in through my account.
So what do I need to
So
do?
all you need, if you can log in through your laptop.
Okay.
Project was the hard part. The project was the hard part. Everything was hard, man.
Just give me a second. Yeah. Give me a.
Yes, please. I prepared a bunch of jokes. I think they'll all fall flat. Though.
No. We'll give you extra laughing time. No, this is my approach. No, I think.
So if you can go on Slack and just click on the link and it will automatically.
Yeah, so you can go to Slack.
Yeah. Yeah, this is all we Then I went in. I don't know. Thank you.
Yeah. All right.
So now I can close myself.
Yes, yeah, you can close yours. Share screen. Screen 2, right?
Okay.
Screen off, and then.
Yeah, question. Somebody had a question. Yes. So yeah, right. Lovely project.
This was the
Yeah,
worst.
no, I think you should write something, but I can tell what it is. And then, you should write something so that other people can't tell. In fact, that's you guys, how many of you know differential privacy? It's like the biggest thing, okay? How to make sure that you give the data out in such a way that it can't be reconstructed. So if you know the databases, if you have a view on the database that are being given, if I give enough of the views, can I reconstruct the database? If I can reconstruct the database, then the security is blocked. Okay, so it's a pretty hard design problem. Well, in this particular case, if you actually leave your column empty, that would give away. So yeah, I think you should write something. Okay, and anybody who looks like they have written too much, it must be Asha. So that's like the second order thing. Okay, so let's go with that, and let's have Dion do the first presentation. And first, let's give him a applause just for reading and going.
Preface, I don't deserve that. Anyway.
No, that's what you do in the beginning.
Okay. All right, let me just make sure that, okay, that works. Okay, cool. Okay, so.
And it's being recorded,
Yes,
right?
yes.
You know for sure.
Yeah.
Okay, good.
Okay, so,
Audio is good.
Yes.
Okay, great. Thank you.
all right, so this is my project, adapting an AI player for Filipino style mahjong. Just to introduce myself and to clarify my identity for the instructors one more time, my name is Dion. And let me start this presentation off with what is mahjong. I'm not going to go through everything on this slide just because it's a general background for what the game is, but essentially it's a tile-based game that originated in China and is a strategy game similar to poker. And yeah, if you'll humor me for a second, before I went to this slide, can I get a show of hands? How many of you actually heard of this game? Okay, how many of you play?
I just saw her playing Prejudice.
Yeah, exactly. So yeah, if you watch Crazy Rich Asians, it plays a part in the climax of the movie, and that's about it. Okay. So we bring it to why I chose to do this. There's a substantial lack of players that I noticed raising their hands, and makes me really sad because Mahjong is a fun game. This is actually done as a part of my honors contract. Dr. Rao is the committee member for it, and he's agreed to help me with an AI implementation because my plan is to eventually make a game out of this with both multiplayer and single player functionality. So an artificial intelligence player would be required for a single player portion. Yeah. And the reason I'm choosing Filipino style, which probably no one has heard of because none of you are Filipino, is because it's simpler to learn, and I'll get into that in a second. Okay. So a small gameplay overview. Essentially, it's similar to card games like Crazy Eights, where you continually draw from the deck and have to kind of play tiles. The difference is instead of a deck, there's a big wall of tiles that you draw from. And then each player turn consists of drawing a new tile and then discarding a tile from their hand. I'll get a bit more into this later because the actions are kind of an important part of what an AI agent has to consider. And to win, the player has to declare a full, usually 14 tile hand of winning tiles, and is generally composed of 4 melds and a pair. I'll get into what a meld is later, but you can think of it as kind of like a group of tiles. Yeah, I'll leave that on for a second. Because I will go into some more of this information later down. Okay, cool. So player actions. This is something I'm going to go a little bit more in depth to because it's kind of important to the implementation. I have it listed in a kind of strange way on this table here, but just know that the actions are the kind of like middle ones. So I'll go from the top. I have them listed in different languages based on what you might know the game as. The top one is to declare Mahjong, which is to win the game. And this takes precedence over literally any other action that you choose to do. And in order of going down, these are the orders in which actions can be taken. So an order at the top would be able to be declared, be able to overwrite someone else trying to declare a different move. So a gang is to create an open 4-of-a-kind meld. And you can see I have a graphic there to show that the meld is just like a 4-of-a-kind, like in poker. A pong is to create a 3-of-a-kind meld. A shi is to create a sequence that is of the same suit, but of numerically increasing order. And if you don't choose to do any of these, you just draw a tile from the card. I have the conditions by which you can perform these actions listed on the side there. You see stealing out of the player's discard or stealing the previous player only's discard. So after you add a tile to your hand, you get the opportunity to rearrange your hand. And during this, you can declare a hidden gang, which is just to declare a 4-of-a-kind, but without revealing what it is. I suppose I should have said that if you declare a meld publicly, it goes away from your closed tile hand and moves into like an open state, which contributes to the visibility of information in this game. And lastly, once you do all that, you have to end your turn by deciding to discard a tile. So that way, when you grab a tile, you'll always have to discard an existing. Okay, other rules. These are just some general rules. There are some bonus tiles which probably don't need to be considered in an AI implementation because when you draw them, an automatic process happens. And the specific rules to Filipino style is that the hand size is 16 rather than 13. So you have to focus on getting more melds than usual. And winning tens can only take the form of 3 of these. This is different to more common styles like Chinese and Japanese, where there are 30 plus winning hands, each of which giving a different score value. And unlike those, there is no different point value. All of these pretty much have the same score. So I'll leave it at that. Okay, this is the research I had to do. These are 5 publications that I have found that detail an AI implementation for Mahjong. The reason there's only 5 is that I can't read Japanese, so I can't include the rest of the publications. I would talk about this, but it also was really difficult for me to understand, I'm going to admit. But going down the list, you can see that each one uses different amounts of like supervised or reinforcement learning. The most successful one and the one that like comes up first and foremost in your Google search feed is Suffix or Super Phoenix, which is the fourth one, and was developed by a team of researchers at Microsoft and and manages to beat most of the top ranking players on an online module site. So yeah, I will leave the Suffix thing. And if I had to make a comment, you'll notice that reading the description, all of these take different ways to encode the game state, and all of these use different methods of training the agent. Mahjong is inherently a complex game. That's the unfortunate truth that I've learned from trying to do this project. And so there's no real best way to approach it, unless you have a lot of money like the people at Suffix have. But I don't. I just have a simple gaming computer at home. Okay. So, and now we go to the kind of embarrassing portion of my presentation. I have this labeled as approach because I use the term project to describe this work loosely because it's nothing more, to me, it's nothing more than a glorified paper. So to start with identifying the things an agent has to consider, I first tried to identify the inherent game properties that Mahjong has that work in an AI state. So at any point in the game, you can see all of, a player doesn't have vision of all the tiles in the game because some of the tiles are owned by other players and some of the tiles are still hidden in the wall. And that's part of what contributes to the partial observability of Mahjong. The actions that I've detailed in previous slides are instant and uninterruptible. They can be there is precedence over actions, but generally these actions cannot be interrupted at a later point in time. And if you consider it from like an atomic point of view, they're just instant. So the game is sequential. And any observed state that a player could have contains the entire history of previous actions. So essentially what you can see as a Mahjong player is your tiles, any open tiles that other players have, and the entire history of discards throughout the game. So judging from this, any action that the player takes in a state, any future state that the player can get to really only depends on the information that they have in their current state, which is why I've stated that the game Mahjong has the markup property. Okay. So we'll go to actions. Here I've shown a small like decision flow of what the agent should do. And it covers the Pong, Chow, draw, and discard actions. Again, you can choose to, for Pong and Chow, you can choose to do these things. When a player discards something, you don't have to take it. But the reason I don't consider the other actions, which are Kang and choosing whether or not to declare a win, is because in Filipino Mahjong, there's no scoring system. So any hand that gives you a win just wins you the game. So you should do that yourself. And for the Kang, it never really comes up that often because there's only one possible four of a kind for any specific tile in the game. So it's usually beneficial for the player to just declare that as it contributes to the information that they have in their state.
So at most 2 minutes after I gave extra time because it's part of the
Okay, that's fair.
so you guys don't realize how quick it is.
Yeah, that's fair. I think I'm almost done anyway. So yeah. So then the actions that need to be learned are just these. Okay, so this is the last approach side, an idea for implementation. Here you can see a nice chart that I've stolen from Rao's slides. I decided to use a partially observable MVP in which the state and the belief states and the actions are defined there. And to inform the reward function, I found an algorithm online that was a modified form of Monte Carlo tree search that accounts for imperfect information. And my intent is to try and use that for the reward function. So let's talk about this. Getting the agent work. You might notice that at this point, I haven't shown anything for this agent. That's because one, I don't actually have a medium in which to test it in because I'm doing this in the Unity game engine. And I would have to create the entire game and then implement the AI stuff. So at this point, I'm not exactly sure whether the proposal in the previous slide is applicable. Just because, sure, you have a Monte Carlo tree algorithm that accounts for imperfect information search. But the thing with Mahjong is that it's so complex that the state space is just so big. And that would end up having extremely large computation cost. So for future work, I'd have to either commit to an RL planning method or planning method and do a lot more research, as well as collect data, or just use a simpler agent that doesn't fully consider opponent decisions. So that would be, greedy, and suboptimal, but it would work. Other things could be possibly factoring in score. I know that I said there was no score in the previous slide. That was just me lying to you. There is some form of score in the sense that Mahjong is used as a gambling game, so there's a score in the form of payout, but this is inconsistent across different players, which is why I've elected to neglect it. And collecting data, because since Filipino Mahjong is unknown outside of Filipino communities, there is no real data to use to train any kind of machine learning agent on, unlike Japanese, which has tons of data from top players. Okay, challenges, game complexity, I've covered this. Mahjong is an inherently complex game with many things. Lack of data, I also talked about in the previous one. Complexity and implementation is me not really knowing how to implement it alongside an actual game interface. So I'd have to learn two things at the same time. And you notice that I have a joke last thing here. That's me. The joke on this slide has been presenting to you for the past 15 minutes, pretending that they understand what they're talking about. So yeah, and as a last required thing on the report, you'll find a more in-depth and objective discussion on the research that I've done and the approaches that I discussed. The content and structure may differ for clarity and complete thought, and just to remove a lot of the jokes that I tried to slide into this presentation, but it's overall a more in-depth, you can consider it a glorified paper review that we've had to do for this class, except with multiple papers. So yeah, these are my references. I know we're supposed to open it up to questions, but I have to warn you that if you ask me a question, my relatively low self-esteem will go even lower.
Actually, we don't have much time for questions, so unless somebody really wants to. Okay, here's my question. Okay, I have nowhere to go. Okay, I can be here and everybody can, do the presentation that's required. And I know that we people have actual exams. So if it's okay with you, I let people take 10+ minutes and then we will be late. And that way you will be happier. No. Anybody who has anybody who has an exam after this? No, no. Okay, so any show of hands whether you want to do that. But
I have work after actually.
no, you can leave. If you have work, you can leave. I mean, a work or exam or something, you can leave. But I mean, my point is, if most of the people would rather leave at 4:30, then I should keep to 8 minutes. If not, I'll give extra time, and then essentially the people who have to leave at 4:30 can leave. Is that okay? So we'll glare at you, but that's fine. Is that okay? People, please raise their hands as people who it's okay, so that I know that it's actually a. Okay, fine. Then, is there any question for you?
Yeah.
So for the company, is there any are there any major constraints you want to with your code reading level? Because C# can be heavy.
Yeah, I think the concept of being able to so for those of you who don't know, the Unity game engine uses the C# programming language rather than Python, which I'm sure most of us are used to using for machine learning applications. That's probably something I'll have to learn as well, just because I'm not very familiar with the existence of what open source, at least, machine learning libraries can be used in C#, and B, how that would affect for example, the load that creating an actual game would put on the system that you're playing it on.
As you mentioned in the literature review slides, there were other existing methods as well, like subjects. So they were implementing some domains which have an implementation of Mahjong, right? So is it possible to use that for this implementation and get a board in other?
Yeah, there are different a lot of these detail like different abstractions of how the game state works, and each of it approaches it differently. Specifically with the ones that use convolutional neural networks, they abstract that domain in a way that fits the neural net that they want to use. So honestly, like the complexity of Mahjong is such that at least what I learned from reviewing these papers is that there's no like, how do I say this? There's no right way to go about it. There's no wrong way. There's just really, really expensive ways. And yeah, and I did attempt to use, in some of my approaches, I do attempt to use some of the information from these papers about the domains, like with the action model, for example. That's somewhat inspired by the one used for suffix, and with some changes like relating to the reasoning that I gave. So
Okay, no, let me cut it right now. After him, this is basically what actually happens in conferences with even faster cutoff. Okay, and they say take it off the line, take offline because the conference they will continue. Here only nothing after the. So please do. I mean, this is again for the rest of the people coming. So thank you. For the rest of the people coming, remember that this is supposed to be an advertisement to make people read your report. Okay. And then if there are people who have questions, they should seek them out and see. That's the whole point. I mean, I understand you won't get points for that, but life is not all about points. That's it. So, okay, so Dan is done. Next, who wants to go next? Joshua.
Okay. So. Browser an edge. Chrome.
Sorry, just a second. Yeah.
You're good, bro.
Next one. The first one, right?
Yeah.
Is it the, okay, that's the
Mhm.
PowerPoint, okay. 1 second. This way, I know why I don't want something. Okay. And- Yes.
There you go. I know what you're thinking already. Wait a minute. That doesn't say grid world. Well, we'll get to that. We'll get to that. There's a very good reason why that's not grid world.
Just so you can grade us, it says grid worlds instead of the D on
Yeah.
the form. But yeah.
We're the first one. So we did Q learning and max Q on a taxi domain. Here we'll have a brief overview of some of the sections of our paper, including like introduction, the related works, Q learning, max Q, experimental results, some of that, and we'll go through it. So
Yeah, so the primary objective of this project was to explore how hierarchical abstractions work out in reinforcement learning, and whether we actually gain some kind of advantage by using them or not. So basically, going through whatever Dr. Rao talked about throughout classes and seeing it from a practical point of view. We explained this slightly before we get to the taxi domain, but the taxi domain is extremely simple. It has a task of picking up a passenger and then dropping them off at another point. So you can break that task down into 2 subtasks of getting the passenger and then dropping the passenger off, and you can break that down further. So this is the abstraction that we kind of use for that. That is a tiny map of what the domain looks like. The R, G, D, and Y are the locations where you might find the passenger and where you might drop them off. The yellow thing is a taxi. We initially wanted to do this with the Good World one, but we kind of realized that there's not many abstractions for us to explore,
if any at all,
if any at all. So,
we have 4 actions: north, south, east, west.
so we instead chose to, we could have done it with Good World. We could have just drawn a line through the map and say, go from left map to right map. In right map, go to goal. We could have done that, but this just seemed like a far better problem to explore the idea.
There's actually a lot of work on this. This is just a couple of them. including the original foundation of what Q learning is, the idea of max Q, which was created a long time ago, actually. The first max Q was, I think the paper was cited 98, 99. So like hierarchical learning is not new. The idea is pretty old, actually. We just keep trying to like make it better, which we show here with this funny, where is it? The learning representations and model-free hierarchical reinforcement learning. It's just a take for continuous domains, which you can't actually do in Q tables. You have to do that, or rather, it's better to do that in like a DQN. So you can get to the full range of real values. You have to send it through convolutional network, otherwise you have like a massive network of this table is enormous. It's like impossible to explore. I tried it. It's awful. So we use just a basic Q learning, greedy as it gets. I'm gonna look one step ahead. That's it. There's 6 actions per state found out, and just this, there's like 500 states you can go to in just this very tiny map. And we used a basic Bellman just for the Q value update.
Max Q, again, we did this in class. It's a basic hierarchical abstract reinforcement learning agent. It's extremely similar to the Q learning system. It's based off of that. The way it works is it decomposes an MDP into 2 smaller functions. So the value function, the Q function gets decomposed into 2 smaller things. One, which represents the utility of making an action in the current state. And then you add to that the utility of completing the parent goal, or the overall utility of what sub goal you're trying to achieve. So that's how it's decomposed in Max Q. So it's extremely similar to Q learning. It's just that tiny decomposition that makes it a bit different.
So now we're kind of through like the general gist of like what max Q is, how we got there, how old it is. Let's get to why we care and some of what we found. And this I think will be the interesting part. So if you look at our basic Q learning, we used OpenAI, their gym for it, and we will just look at the basic Q learning. You'll see it follows a pretty stable pattern. One epoch, it goes really, really bad. As you train it more, it gets better and better and better, and it minimizes the amount of negative reward that it's going to retrieve. This looks pretty standard. I'm sure we've all seen something like this. When we look at max Q, you'll see that it gets wildly varied and sometimes spontaneously just dies. Which begs the question, does this actually help us? Does breaking it down into these hierarchical structures actually improve our performance, or is it just for our readability? Because this variety, this varied outputs really changes heavily. We would run this like 10, 20, 30 times, and sometimes I just get a wall of like bad epochs. And sometimes I get a perfect line. And there's that's weird to me. So what causes all this variance? What causes the agent to sometimes go really, really good and then sometimes do really, really bad? Or what would fix that? Well, we're using a very greedy policy. It's just one step look ahead. So maybe just a heuristic might fix that. Or maybe we need a more complex domain. This is a very simple domain. So maybe the 2 abstractions isn't enough to really show the benefits of that. And maybe if we had defined our abstractions better, because we only have 2, maybe it's the fact that we have these 2 very explicit abstractions that's the problem. What if we make its own abstractions? What if that helps? So there's a lot of questions with hierarchical task networks, and the whole section that we just start generating questions off of just these results of why is it so not great?
So we spent about a month basically exploring Dr. Rao's skepticism and verifying it in relevance to abstractions and their use. And we definitely feel that we could do more with abstractions in that we could test this out in more complex spaces and continuous domains and see how that works out. One interesting thing was, again, like Josh just mentioned, variation was insane, and in most of the cases, on average, it was mapping the Q-learning agent. A lot of the times, it was just doing a one-to-one thing. Now, a note of caution would be that maybe our implementation wasn't the best and something we could definitely work on, but with time, that's something we would definitely do.
If you want to read the full report, you get a better description of what we did, our methodology, a deep explanation of how we got to where we did, what we found, a more robust discussion section, and future works, I think is the bigger question of like, where do we go from here? If we're not sure whether or not max Q is the way to go, there's like 20 different ways to take abstractions. We can explore all those avenues. So we mentioned a couple of them. So that might be something you're interested in if you think abstractions could be beneficial. And here's our citations.
Yeah,
For
that's
that.
it.
Okay, so we have time for questions.
Yeah, I have a question.
It's us.
So, in the paper, the MaxQ original paper, also they did taxi domain experiments.
Mhm.
They were able to actually outperform flat Q learning. So, was your taxi domain itself different from the one that was in the paper?
It definitely would be, because this is done using the OpenAI gem.
I understand,
So,
but like effectively it was
effectively,
OpenAI implemented.
Yeah,
that as
so the thing that
taxi
was-
domain in that.
so the thing that I found interesting was, anywhere I looked, first of all, the 1999 paper, 1998 paper, they didn't reference any of the code that they used.
And
They did it practice, and we don't know how they verified the results that they did. They had lots of math and proofs in that, which made sense, but no code to back that up. A lot of the other implementations I found, they were all made using the OpenAI gem. And I did find another one, I did run it against my own, results were surprisingly similar. And we had similar results with the cube. So I think one area that we definitely have to work on is to see what kind of parameters we're using on the inside, and if there's small changes we can make to improve.
was your domain stochastic or did you use the deterministic version of,
I think it was the stochastic. What do you mean by,
like, in the paper's version, if you take an action, there's an 80% chance it goes.
no, it was deterministic. Yeah, so we were using a deterministic domain. Yeah. There were two versions of MaxQ implementation. There's MaxQ 0 and there's MaxQ Q. We use the MaxQ 0 implementation of this one.
Any other question? So, okay, go ahead.
The level of granularity you think that is your max capability, like if you were to decode an HTM into like say, it assumes atomic state action.
That is something, I think this one does do that. So at the end, you have to deal with atomic level representations.
Granularity.
Okay, so I can, if you want, I can explain really quickly how it represents things. So you have a Q state and you have a max state. The max states are the ones which represent what you can do. A Q state just says this is a sub goal and this is where you live. At the end of this, when you resolve, so the documentation that we did does mention exactly the value function and the Q value calculation equation that they use. It's extremely different for primitive states and for composite states. Composite state meaning the combination of primitive states, right? So you have to condense it down at the end. It just boils down to it using those subsets. The idea is more of like a temporal abstraction, in that I don't have to think about the destination, the final destination of the passenger until I pick them up. And I don't have to think about the initial like passenger pickup point once I pick them up. So that's what we're trying to force. So you do have a certain amount of atomic representation.
Okay, thank you, guys. So, who's going to go next? Yeah, you have to go. Yeah, okay. And then next, anybody who have, any of you have a time problem? You have a time problem? What is your time problem? I have. Okay, okay, fine. Yeah, I don't care about, because the valuations are over, I can just ask.
It's on top.
Yeah.
It's on the top. Oh, that's it.
I don't have any nice.
Okay.
Okay, good. One other thing, as I setting up, the RL experiments are notorious for replication problems. Okay, so in fact.
Yeah.
So that.
One of them is the presentation, one of them is our report. So that's the report.
Most of these are huge, averages of large ensembles, and so, and even then it doesn't actually show. In fact, I think there was even a machine learning replication price.
So,
The RL training
you
problem.
might want.
So that's something that you want to keep in mind.
I
Okay.
Yeah, I think you might have to probably just move down, up and down also.
Okay, it's up and down.
Yeah, just up and down.
Okay.
Yeah, you can.
Yeah.
All right, so very good afternoon, we're all here. We will be presenting our topic of exploring arbitrary query crafting and optimization of goals through domain specific planning in Dungeons and Dragons. 5E means multi-classing and
It's fifth edition.
with the fifth edition?
Yeah.
Oh, yeah, I'm sorry. Okay, fifth edition. And through this presentation, we're trying to advertise our domain specific custom planner that we made that takes in the users info about like their goals, their preferences, and their needs and requirements, and like outputs of a state, like a sequence of decisions that the user would have to make in order to like attain that goal. So next slide.
Okay, so we'll start with some brief introduction. If you're unfamiliar with Dungeons and Dragons, it's a very popular tabletop role-playing game. Each player has their own character. And while there are plenty of reasons to make your character the way you want, often customized, often you have a specific vision in mind. Like I reference a Fate character because a friend of mine, he is making his character as close to Dr. Fate from Black Adam as he can. He is doing every decision to be the same. Another thing to factor in when you're considering creating your character is that most campaigns will end before level 20. So if there is a specific class feature you want to be able to have, you want to be able to try it out, you can't assume like, oh, if I'll reach it at level 20, that's fine, because there's no guarantee that your campaign, that your game will last that long. And with these rule restrictions in mind, if you have multiple competing needs and you know that there's going to be a time limit, it's not very clear on how to get all of these different things, especially as they compete with each other. As such, there's the hobby called theory crafting. It's pretty popular on Reddit, where you try to make a character that completes all the necessary goals within the restrictions, but it's not as focused on creating a playable character as it is just meeting the goals.
So theory crafting and multi-classing. First of all, theory crafting is a way through which people try to analyze what the underlying mechanics of the game is, so that they can come up with various like optimal strategies and policies with which they can boost their gameplay, or they can make a character that's like really optimized to their needs and requirements. So multi-classing is a way through which people analyze the mechanics of the game to find and develop optimal characters to improve their gameplay, especially if the character is not intended to be played. Multi-classing gives you some features. You can like read the benefits of different classes at the same time that like being inside like only one class wouldn't allow you to do. And what you do is like you take multiple levels and multiple classes. Multi-classing has always been a topic with a huge variety of players exploring different strats and creating different policies for successful goal-oriented character development. So our motivation came from the fact that a lot of people do this thing of like multi-classing and theory crafting at this point manually. This is really, really inefficient because like, there's like multiple rules to go through that Dungeons and Dragons has, and it can like leads like very, very complex situations. And because of this reason, like, most of the time these manual plans tend to fail. And a plan that would be like, termed as an optimal or valid plan as of now is gonna be deemed like inoptimal, non-optimal, or like invalid, like probably like in the next couple of weeks or so. So what we try to do is like, we are trying to automate this manual process. What we've done is like, we have created a custom domain specific planner that can take in user goals and preferences and output a solution that's a sequence of decisions. What levels to take, what classes to be in, what subclasses to choose, and how to like arrange your stats. And then the user can provide an arbitrary goal with their desired rules for the story casting challenge.
I'm gonna add, because we have a little bit of extra time, that I just wanted to, we originally trimmed this out in the presentation. But one of the things that inspired this was that there was a very popular build that was going around where it's monk in heavy armor, which for those who have played the game know that monks are very counter interactive with heavy armor. It disables most of the things you want as a martial arts master. But the original poster was like, look, I have the statistics to back it up. This is something that should be very viable. And then a week or two later, someone's like, wait, you forgot this number. And then it turned out that, as one might expect, if you are trying to master the martial arts, you should not be wearing full plate armor. Our implementation scope here is we are limiting ourselves to the source reference document, which is all of Dungeons and Dragons that is not copyrighted, so it's very limited. And we use all the rules there to create some CSVs that function as a rule bank for all of our decisions. We have a variety of feature matching tools that we created that combine various class features and subclass features, the various spells, ability score increases, and level ups to create a character that is able to be coherent and is actually one that is for certain playable and is able to meet all of our goals. Did I click it? Yes, okay. Yeah, we search through the CSVs, which contain all of our information, and then we use the feature matching script, where for a given feature, it lists every possible way to get it. And then for all of the features, we explore all of the different ways, but because many of them would conflict, like if you want a strength saving throw and a, actually, I guess that, if you want a dexterity saving throw and a wisdom saving throw within 4 levels, you're not able to do that given the contents in the source reference document, because those would require conflicting starting classes. So those two would not be able to be combined. So there's a lot of ways where you have all of these different paths to features, where some are able to mesh and some are not. And this is used to determine which ones are. And then for all of our final plans, once you have created it, we give each a grade based off of the number of classes that aren't progressing any of your goals. Some of these classes are introduced because they help you meet the prerequisites for your goals. But if you don't actually want to play as those things, if it introduces a whole bunch of fighter levels, but you're hoping to be this cool wizard, it's going to give you a lower score for that class plan because it's less of what you wanted to actually do. With -20 as all 20 levels are in things you don't like, and 0 is everything is progressing your goals. This is the output. It is very wordy, and I will instead show you the output in an example where I am able to explain it. So our example here is that our only goals are, we want the Draconic Resilience feature, which is given by being a first level Draconic Sorcerer, and we want to be able to cast Eldritch Blast using Charisma. That is very accessible if you're a Warlock. There's also a path if you're a Bard. And so we're going for the sort of Dragon Cultist sort of vibe. But unfortunately, our stats are 10 across the line, a 13 in Dexterity, but a pitiful 7 in Charisma. If we want to be able to take levels in Sorcerer as a Warlock, we need a 13 in Charisma, which means +6 more Charisma. And the same goes the other direction. If we want to take levels in Warlock as a Sorcerer, we'll still need a +6. So we need to get +6 somewhere. Our story ends at level 8. So we aren't going to get further than that. For both Sorcerer and Warlock, you're only able to get a net of +4 from ability score increases by level 8. So getting to that +6 is going to be very difficult. We refuse to be a Half Elf, even though they have the highest charisma bonus available in the source reference document. And we want to be able to speak Elvish. We're very needy and picky, and we have created perhaps one of the most difficult scenarios if you're trying to create a character. But you are the least set up for it. Everything you want to do, you are in the worst conditions. So our example input, you're able to put that in. You say, I want draconic resilience. I want to be able to pass Eldritch Blast with charisma. I want to keep Eldritch. We have our initial stats, which we set in the previous slide. We have no requirements for any specific classes that are all 0. We have no need for extra ability score increases. Our total level is 8. Our first level, we don't care what it is, -1 is null here. And then we say we don't want half health and -1 is null of, we don't care what kind of half health, we still don't want it. So now let's run make characters and our results. So in order to be able to do this, there are exactly 2 ways. We take 6 levels in Python. The first 4 will give us +2 to charisma. The 6 will give us another +2 to charisma. Because we start as a tiefling, we get a +2 to charisma. So that gets us our +6, so that our 7th and 8th levels can either be in sorcerer, a 9, or a 10 in warlock, or the other way around, the order doesn't matter. But that is these are the only 2 ways that you are able to, using the contents of the source reference document, be able to create a character with this. Our final stat line is given here. Our remaining unassigned features are here. This is us saying that it has to be a tiefling, we don't care what kind. Here, it's saying that we have to be the first subclass for sorcerer, which is draconic, because we said we wanted draconic resilience. So we have to be a draconic sorcerer. But we don't care what kind of warlock, because all warlocks are able to get Eldritch Blast. We have to be an acolyte, because that is going to give us access to the Elvish language, which is our request. And then we have no need for feats, and we get a score of -6, because we wasted 6 levels taking fighter, even though none of our goals were about being the full fighter.
So, conclusions, the Python-based domain-specific planner was able to give us like point answers. For each, like, any kind of like, variation of user input. Thus, the theory crafting, multi-classing was successfully explored using like a Python-based domain-specific planner. We tried using the PDDL one but we couldn't like implement it that much because it was extremely, getting like extremely complex. These are like very.
There were about
Yeah.
a half dozen states per option, and when you get to having 12 to the 20th options, you start being like, perhaps standardizing this and not using PDDL would be a preferred way.
Yeah. So we stopped using that and then we like just created like custom based Python based one. And then all rules were mapped using fifth like source reference document into the CSVs. We use like multiple helper functions to like extract all the information from the internet, put them in a tablet format so that it can be more readable and trackable. And algorithms were used to track and record the information stored in them so that the various helper codes can like import them. The helper codes were used to extract information, as I said before, and this was mainly used by the feature magic script that has all the rules in it, as like what kind of features are available for the class at a particular level and what kind of spells and all that. Given the user's inputs, the plans are generated by the planner with a grade that represents the optimality of the plan. And greater the negativity, less is the optimality. So for future work, do you want to go?
Yeah, sure. Our future work, we would like to explore an alternative way of PDDL. If there was a library that we're unfamiliar with, we looked through a fair bit and explored all the ones that our local Python PDDL components were able to run, so we weren't able to see something there. But alternatively, if we were able to use PDDL for certain components of this, we weren't able to incorporate the fact that some features entirely subsume others. If you wanted access to Find Familiar, there is an improved Find Familiar that is available for Warlock. But if you are searching for Find Familiar, it won't suggest the improved version that you can get as tactical change. But using PDDL could be great for exploring that some things are entirely subsumed within another. And would allow us to standardize more things so that we could explore beyond the SRD without having to modify the Python code. And then implementing a craft data structures for the same purpose if we determine PDDL is the best way to approach that.
So in the report, you can expect all the background information on theory crafting in Dungeons and Dragons, especially multi-classing, and examples for every rule is mentioned in the report too. And then you can also find the rationale for why a player may want to include an option or ban it. The report also has an in-depth explanation of the methods that we used and all the codes, the helper codes that were made to build the planner. And an in-depth explanation of the programs as to what to do and how to perform, what kind of information to take in, and what kind of outputs they have, and how those outputs are taken in by the different files.
And then these are our references. We use the 5th edition SRD, and then everything else we basically did from the ground up.
Thank you. We don't have time for you guys for the questions because we can check in minutes. So if you have questions, please ask them separately. Next, maybe, I need to go up, and then who's going off the game next? What's your name? Shyam, okay, Shyam.
I'll be leaving at
Bye.
4:30.
Yeah.
If you want to send me.
While meeting is setting up, you can ask questions if you have any questions for these guys. That's giving you a battle cost in that down. So there's no dead end. Okay.
This is the one, right? Yeah.
Yeah, cool.
Okay,
Hello, everyone. My name is Mehdi. I'm presenting my course project on learning dynamic belief abstractions for social navigation scenarios. So these days, cobots are being employed more and more because they are more advanced, like from cognitive point of view, or like the physical abilities. But so we are facing new challenges. So one of them is that so sometimes because of the inherent limitations of the environment, the safety and task achievability of even some simple scenarios like social navigation can be jeopardized, like in the presence of the human. So we can just look into that more depth. So let's say we have the robot and the human in the environment. This is a really simple intersection problem. So sometimes because the environment is sparse enough, the robot will be able to somehow convey its future intentions to the human with just its motion act. So for example, if the robot wants to turn to the right here, so before getting to the intersection, the robot can start moving to the right, so it kind of like convey its future intention to the human. But sometimes when the environment is confined, the robot's actions are really limited. For example, here, if the robot wants to turn to right at the intersection, there is no way that the robot can convey this information through its motion action because like the corridor here is really narrow. So intuitively, one solution would be employing explicit communication signals coupled with the robot's action. So in this case, the robot's motion actions are going to be explainable for the human. So in this case, if the robot wants to eventually go forward, so it can couple the forward communication signal, which can be just some natural language communication signal with its motion. So the human is gonna know that, oh, okay, so I need to clear the corridor. But it's not really easy in practice and theoretically to do this. So that's why, so in my, like one of my recent papers, I explored this problem. So this approach is called deliberative communication and motion plan. So you can see the details in this paper, but I'm gonna explain it to you briefly. So let's say you have this environment, we have the robot's goal, the human's goal. And the robot, so if there is no human in the environment, so simply robot could employ some sort of RRT or motion planner. So that like the search tree would be like just the motion plans. But here we have the human. We like I explained that why we need explicit communication signals. And if you want to couple communication signals with the robot's motion actions, so the search tree is going to be like expand it significantly because for each motion action, for example, the search tree can have multiple branches with different for different combination of motion plan and communication signals. And even computing the cost function for each branch of this tree is not a trivial task anymore, because the robot needs to consider the effect of its motion and communication actions on the human's behavior. And to do so, the robot has to maintain the belief state of the human throughout the frame. And again, to be able to model the human's belief, the robot should assume that the human's model of the environment. And so the question would be, so how do we want to represent that model? So we can just do a grid discretization here, but the question would be, what if the environment is significantly large? The floor map is significantly large. So if the grid representation here is fine enough, like it's really accurate, then it's gonna be like a lot of computational expenses. It's gonna be like computationally really expensive. And if this grid representation is coarse, then it's not gonna be accurate. And that's not a good thing because we want to avoid colliding with it. So because of this, even though this approach couples communication signals with the robot's motion plans, but still we need some sort of abstraction that humans believe on the humans like understanding of the world. So in my like another paper that I recently submitted myself is still on the review. You can find it here, it's being archived, it's public. So I did some sort of like dynamic abstractions for MVPs. So before explaining how I'm employing this approach for this project, I'm going to explain the approach itself quickly. So let's say we have like a 4x4 grid environment. So dynamic abstract representation method is called DARL briefly. So it starts with a coarse abstraction of the environment. So instead of having 16 cells in this grid environment, it can start with only 4. And this grid word just has like a goal and a pitfall here. So DARL basically observes the dispersion of Q values in the environment and refines the initial coarse abstraction. So for example, the pitfall and the goal, they have significantly large negative and positive rewards. So that's going to give us like some variation on the dispersion of Q values. So because of that, DARL will be able to, after some interaction of the RL agent with the environment, DARL will be able to refine the initial coarse abstraction. So it could be conceptually something like this. So it's going to be like finer around the goal, finer around the pitfall. So this is what DARL does. So what I did in the project, I wanted to like employ this abstraction method for the joint communication and motion planning. So to do so, I had to model the social navigation scenario as an MVP, then run DARL for this given MVP, and then use these abstractions in the original communication and motion planning method. And then I can compare like what would be the result, what would be the benefits of using these abstractions. So this is how I model the social navigation scenario as an MVP. So here we have the robot, we have the human. So the state would be just the location of the robot and location of the human. The robot's action would be all the combination of robots' motion actions and communication actions. So here the robot can go to left, right, forward, backward, and all the communication actions would be I'm going to forward, I'm going backward, I'm going to left, I'm going to right, and silence. So here, for example, we are going to have like 20 actions. And the transition function, so the robot can simply go all the like neighborhood cells based on its movement actions. And also the human does just a random walk, but its walking is responsive to the robot's communication. For example, if the robot saying that I'm going to the right cell, the human is going to avoid going to that cell. So the robot's communication actions affect the human behavior here. And so this is the transition function of both agents, and this is the reward system. So if the human is located here, the robot is going to get like 0 reward all over, except colliding with the human. So the goal would be avoiding colliding with the human unless like until the episode is terminated by reaching to the max step now. So this is how the MVP has been modeled. So the result that I got. So using DARL and using the MVP model that we did for the social navigation scenario, so we can get some dynamic abstraction like this for all different locations of the human inside the grid. So I'm just showing 2 examples here. You can see more examples of, more results on these abstractions in the report. But here, if the human is here, regardless of the location of the robot, DARL gives us an abstraction like this. So it means that if the robot wants to predict the human's behavior, the robot is going to assume this word representation from the human point of view. It is effective because it's fine around the human location and it's coarse otherwise. I mean, even psychologically, it makes sense because we humans like in an environment, we care more about our like closer neighborhood. And we just like don't care about like far away when we are doing some simple like navigation tasks. And also here is another example, if the human is in this corner, we get an abstraction like this. And it works because the environment can be like continuous. Like it doesn't have to be originally like defined as a like tree or something like that. In fact, it is continuous because we are using RRT, some variant of RRT. So how does this affect the performance of joint communication and motion planning? So this is the result. So this is the running time, which like this is one method to measure the time complexity of this approach, and this is like different problem sizes for the social navigation center. So what here we can see, I just compared the original joint communication motion planning method with abstraction or without abstraction. So if we don't use abstraction, we can see that why the problem size increases, the running time increases significantly as well. So the joint communication or human aware planning algorithm that we saw is not scalable to the size of the problem if we don't use abstraction. And that's because like the computational complexity increases significantly. But when we use abstraction, we still see an increase in the running time, but like we have been able to mitigate this problem. So it's relatively more, we cannot say it's scalable. That's a huge claim, but it's just relatively more scalable when we use dynamically abstractions. So we saw that like original joint communication and motion planning has a scalability issue. We saw that using dynamic belief abstraction can kind of mitigate the scalability issue. And also based on the result, we saw that the efficiency of the robots in terms of the travel distances is not going to degrade as a result of using the dynamic abstraction. That is because abstractions that have been constructed are effective and are meaningful. And in the paper, the full report, you can find more information, detailed information on the joint communication motion planning. You can find more information on the belief, on the dynamic abstraction, on the notion of the belief abstraction, definition of the belief, and also like the methodology to model the social navigation as an MVP, and finally more discussion on this. Thank you for paying attention.
Okay, yeah, 11:42. So one question when the next person is setting up. Who's the next person setting up? Okay, go ahead, set up. Yeah.
One results page is the first one. What intuition do you have like where the human was on the left side of it? It was very it was very fine grained versus above it, which was the same distance away from the human. That was very important. Why? What reason?
Because in the NDP modeling that we did, so when the robot collides with a human, like when the robot is going to be like present at the same cell that the human is, it's going to get it like significantly negative reward. Because of that, that gives us some information to do more refinement around that location. And we do that while the agent is interacting with the environment. So after a while, when the agent is like able to learn the MVP, we just say that, okay, so we don't need any more refinement. We can stop here and then we just extract the abstraction at that moment for for all different values for the state that we have. So just basically because of the dispersion of the Q values that the agent observed.
Okay, thank you. Who is going after next? I just want to know the. Okay, the people who have a 4:30 class, have they all taken care of by now? 4:30 class, the exam, 4:30 exam, somewhere else. They're all taken care of by you. So now I'm just going to take whoever wants to take place. So you want to go next? Okay, yeah, go ahead.
Yeah, thank you. So we'll be talking about symbolic deep reinforcement learning. So we have seen a lot of buzz about integrating symbolic planning in deep reinforcement learning. So in this we'll be trying to implement the merits of symbolic planning in deep reinforcement learning. Okay, talking about deep reinforcement learning, you know, like they make use of they are basically black box neural networks that like where the which lacks transparency in the decision making process. And like so, and they are data hungry, meaning they are not data efficient. So we in the paper that we have considered, it tackles the problems by providing a framework which takes care of the task, the subtask scheduling and the data-driven subtask learning which happens and the subtask assessment. So the task level interpretability that we are talking about is done by relating the symbolic actions to options. Okay, so basically the experimentation is done on Atari Monte's revenge. Okay, so talking about the framework consists of three main components. First is the symbolic planner, the controller, and the meta controller. Okay, the planner basically performs like the long-term planning by a series of symbolic subtasks that is accompanied by that is given with the intrinsic goal prior with along with the prior knowledge that is given to it. And this is and then it's passed on as this passed on to the controller, wherein the controller is modeled on the external environment. So basically, the controller makes use of a deep reinforcement learning to learn the sub policies for each of the subtasks. To get to using the intrinsic rewards, and then this is done on the external environment. So basically, after this, the meta controller evaluates the controller by performing an R learning using the extensive rewards from the controller and suggests new intrinsic goals to the planner. And this is a cycle that continues until an optimized optimality is attained by these because all the three of them cross fertilize each other to attain an optimal plan and learns sub policies. Talking about planner, so basically we try to concentrate on each of these components individually and try. So basically in the paper the authors basically use an action language BC and an and a solver and answer set solver Klingo, but we could have also used PDDL based planners which also go well. So basically talking about trying to understand these two planners. Planners built on PDDL perform better on issues with lengthier solutions, and planners on ASP do better on job requiring extensive reasoning to about the action conditions and the effects. So looking at this in support of the ASP that is being followed, the expansion in the number of objects there is not until there is not much grounded actions that are required. It wouldn't cause a problem in ASP based planners. And for shorter plans, ASP planner can be much quicker than PDDL. So that's the reason that this was taken up. But this was something we wanted to we're working on, but we were not able to get to it.
So, as you mentioned, we try to focus on the controller and the meta controller portion of this framework because the ASP and the Klingo solver that the authors used beyond the scope of our expertise. There was a lot of things to learn, but we did try to assess the differences between PDDL and the ASP, but majorly we focused on the controller and the meta controller part. So the controller is nothing but a double DQN algorithm, wherein the specific difference between WDQN and the vanilla DQN is explained in detail in the report, which you can go ahead. But basically, the controller, if you just move back to the framework here. Okay, so once we get the plans generated by the Klingo, plans generated also have something called a row event, which actually is a measure of how the plan performed actually, and this is a way to assess the sub goals once they are out of the meta controller. But the controller, once the sub goals are outputted by the symbolic formula, what we use is we essentially map these subtasks and subtasks to the Atari Montezuma Revenge environment. And what the WDQN does is it takes 4 stacked frames of of the Montezuma Revenge and essentially maps the states and actions using Q values. And once we get the Q values used by taking constant actions, there are actually 8 sort of actions in the Montezuma Revenge, which are simple movements up, down, jump right, jump left, and all that. And we get Q values for that. And once we get the Q values, the controller also has an extrinsic reward. But before that, okay. Okay. So reward that you see here, the first one is actually the intrinsic reward that I talked about, which the controller uses. And the phi symbol is a parameter, a large parameter to encourage exploration of the sub goal. And R is a reward, of course. And once this interacts with the environment and runs and accumulates the rewards over time, we also have something called an extrinsic reward, which is based on a function mapping of that epsilon parameter. The epsilon parameter is nothing but a success ratio in which the immediately previous 100 episodes, the rewards from the immediately previous 100 episodes that we get, and how well that perform is what we call the epsilon parameter. And a function mapping, we just threshold this epsilon parameter to 90%, and the sub goals which achieve well over 90% is something we call as reliable, which are then later pushed to the meta controller as an extrinsic reward. The meta controller then performs something called R learning. This is a simple reward update that we perform based on the row values which we initialized as part of the planner. In the planner, as I mentioned, we did have a fluent specifically to measure the transition of these plans. And a reward learning, when we get the success, we use the success ratios to update that particular row value and get the extrinsic reward. And this keeps updating the row fluent in the plan, and the corresponding sub goals or row value of the corresponding sub goals gets updated as it emerges. So this is something like a model based, a reward based learning for the planner. So we focused more on, the authors actually put forth 13 sub goals for this environment, but we focused on 7 of these sub goals. As you all know, as you all see in this game, there is one optimum plan when the human player plays. Go to the, he'll be in the middle platform, go to the lower right ladder, jump the devil, skull, whatever we call it, and then move to the left ladder, and then of course move to the key. There are 13 sub goals in this, which the authors have put forth, but we focused only on 7 of these, which was a little ambitious. But the results of this was actually that we were able to train it for about 25,000 steps. And out of these 7 sub goals, we were able to successfully learn for only 4 of these, which is moving to the lower left ladder, moving to the, apologies if this graph is ugly, and moving to the left of the skull, and then getting the key location, and of course moving to the middle platform back. So this graph actually mentions the success ratios of achieving these sub goals. As you can see, the y-axis is the success ratios. As you can see that moving to the lower right ladder was achieved pretty sooner, but moving to the left of the skull, in which the skull part is the actual moving part, and it did reach 80% as 80%. It did achieve that task 80%, but it did fall in the next few episodes as well. And these were the other 2 sub goals. So the author's results were actually also trained for actually 25,000 episodes, but the results that we got were able to achieve only 4 sub goals of those. That is something that needs to be investigated further. And what you can find more about this project in the report is more details about the entire algorithmic flow of that, of the project, right from the planner, controller, and meta, and the different components. We majorly focused on the controller part, which is the WDQN, and the reasons for choosing WDQN is also discussed in the report, which you can take a look at. And there is also a comparison with respect to the results put forth by the authors in terms of success ratios, the number of samples, and how it compares with what we have done. Taking this further, what we think is that there was a plan to replace the ASP and Klingo solver and replace it with PDDL, but that was pretty ambitious because but that is something that we are thinking about in taking this project further. And I've also attached the references. I'm sorry, I don't have a slide for the references part, but the report actually mentions a lot of references with respect to the original. There's a close similarity with another paper which doesn't use symbolic planning, but most of the components of this framework is used. But I've also attached a reference which teaches us the difference between answer set programming representation and PDDL representation, and how literals and the relations are defined. So that will be all, guys. Thank you.
Also, please set up and you have just more one question because we take it for minutes. Anybody have a question? You want to go next after this? Okay.
Here, did you at least try to shift the ASP domain into the PDDL domain for the
I actually
planner details for this particular domain?
yeah.
Even the planner didn't work for the PDDL part, but could you at least implement that stage of it, that you had the domain model and everything ready in the beginning?
We did try it, but the controller took most of our time. Controller portion took most of our time, but we did have that as a milestone, replacing PDDL. But we did look into it. But learning about there was one aspect, the row component which I mentioned, which attaches to a fluent to assess the quality. We were trying to investigate how to represent that in PDDL, and that was also taking up a lot of time. So we didn't go any further than that.
Okay, thank you.
Thank you.
One before Costa start, just one general comment about talks. Like one of the things that bothers the academy is that everybody does, so some of you also are doing. Don't ever end the talk with a huge thank you slide and expect people to remember what you talked about. Because your thank you slide is no different from the other people's thank you slide. They're all slightly different font. So if you feel this desperate need to say thank you to people, put it at the bottom of the summary slide. You understand what I'm saying? You have to help people remember what you just said so that they can ask questions. You put a thank you slide, you're asking for too much cognitive load. It's just a small hack. Avoid doing this. Okay, go ahead.
So how much time?
Basically, 10 minutes is the nominal time. What you can do.
Thank you. I tried to do it. So yeah, so this is my project by reason. Like PyTorch. It's as you can probably guess, it's a software. So this is on the bottom of the first page that you guys have, slightly different name to what you have. So what's the motivation? So coming into the class, obviously I was interested in planning. I had to talk with professor. He was like, what does planning mean to you? And I thought that I don't really know the answer. So I have learned that. On the other hand, what was interesting to me has always been is like, when we make decisions, we make very logical decisions. So at least that's what we think we do. But if someone comes to the office via cab and someone asks, hey, why didn't you drive today? They'll be like,
hey, my car had broken down yesterday, so I took it to the mechanic, and it's at the mechanic, so I took a cab. And it's like there is a clear logical structure to the way we reason and when we take decisions. So I wanted to so I was kind of frustrated with many of these black box models, or in general models not having a very strong why in a similar logical structure. And this is my attempt to build an open source software. It's on GitHub. All of you can access it. Hopefully you will, some of you will. Actually, I committed a hello world yesterday night, so maybe that will get you started as well. So I'll come to what it does. So, but basically it's an explainable inference software using logic, and then I'll touch upon how we can implement it or apply to planning and RL domains. That part I couldn't finish up in time for this presentation. So I'll start with the framework and then look at the stuff we talked about. So just a refresher on logic for anyone who's been out of touch for a while. So propositional logic is something like this. So if Jack has school and school starts at 7 a.m., so Jack wakes up early. So this is A and B gives C. And the operators are as you see on screen, which is not, and, or, implies, and if and only if. And then the atoms can be either true or false. And then I move to first order logic, which is what I'm using, which is also known as predicate calculus. So what's a predicate? So in this example, like a friend could be a predicate which takes two variables. Then you ground the variables. We call it grounding, basically replacing it with constants like Jack and Phil. And then we get the big sentence, which is Jack and Phil are friends. You switch the arrows around, and that's how you go from a sentence to a predicate in this software or any first order logical structure. And like I said, this process is called grounding. So whenever I say it's a non-ground atomic proposition, it's basically predicates plus variable symbols. And if you have constants, instead it's a ground atomic proposition. So I'll be talking about maps a lot. So how does predicate calculus work in maps? This is like the simplest example. So you have a kind of a directed graph, and then the constants are like the nodes, and then you can have a predicate coupled with a constant, which is like location C1 could be how it's a unary predicate, and you can have a if there's a path between two locations, then it's like path C1 comma C2 could be a binary predicate. So what I have here in PyReason is generalized annotated logic. So basically what it does, it does reasoning, but with first order logic, with also support for propositional logic statements. And we can annotate, I'll come to what's annotation in a moment. We can annotate each of these, which is basically mapping into this interval of zeros and ones. And what this tree represents is that if, let's say, something's annotated with 0.7 to 1 at some point, let's say, what's the like me being present in this room in half an hour's time is, let's say, 0.7 to 1. Probably will still be going on with presentation. From there, as we get closer to the 30 minutes, we'll probably go further up the lattice, but it's unlikely it's suddenly going to go from 0.7 to 1 to 0 to 0.3. Right, so it's kind of a way to tackle with inconsistencies, mostly something the users don't have to deal with, but it's documented in the repository, and I have more slides which I cut out to explain that as well. So annotations, how does it help? So first of all, like I said, it's a mapping. So whatever you see in yellow with I'll explain what that is. So at is here a binary predicate. MU is short for memorial union. So what I'm trying to say here is that, hey, if I have no information about Jack being at memorial union, I can represent it as at Jack comma MU 0 comma 1. And that 0 comma 1 is a bound. That's what we are trying to map to. And then we are also supporting the propositional pieces within this. So when I say I don't know, it might be they are there in at MU, and then it will be 1 1, and then if they're not there, it will be like 0 0. So that's what I'm talking about, and this kind of thing also
assures that uncertainty thing. And as you will see later that this also goes and helps when we're trying to implement it planning domain, that how do we model states which are like partially observed or we don't know everything about. Or even in cases like, let's say you saw me walking towards the Apache Boulevard, and then you came to the class and someone asked you where I am. So you will not be sure whether I am at MU or not or somewhere else, but you will probably give it a greater certainty measure for me being at MU as compared to being at the stadium. So these kind of things, which is a very real domain kind of things, can be modeled in this framework. Also, yeah, it supports temporal reasoning. So again, like continuing with the same example, the first thing in yellow, it says that Jack was not at MU at 10 a.m. So you include the time component within. If we don't have any information about a certain time, we can leave it at uncertain. And that's the open world assumption. Yeah, that means I have completed 7 minutes. Timing myself, temporal reasoning. That's the open world assumption that anything that's not specified becomes uncertain. So you only need to specify what you know whenever you're implementing this. And then if you know about Jack at 12, then that's 1-1. So this is like the structure. You have some initial interpretation, which is basically the kind of what you start with the initial state, as we know. You can have some other facts. Like say, for example, you know at 12 o'clock today it will rain. So that can be something in a future state, but you have a prediction, something like that. You have a bunch of rules, which I'll come to in a bit, and the graph of the place, and then you get the output, which again I'll show. And the important part is we get explanations. Again, I'll show in a bit. Not much time. So this part I'll show in the example and talk through. This is like the general structure of the rules in a very pure logical terms, all the stuff it supports. Yeah, this is something type checking similar to PDDL. Again, not going to go through this. I have this so that if anyone asks any questions. Yes, so this is what I want to show, that we know this map. This is the ASU campus. To show an output for today, to show like what kind of stuff we can do with this. We start with the map. I manually annotated the intersections and took 5 buildings, the Brickyard building where we are now, there's GFC, the Gamage Auditorium, and a couple more, I don't remember right now. And then this is like a visual, which is a work in progress, but once we model it, this is what we have. It shows pathways, it shows what's connected to what. And then each pathway has all these attributes, which again you can read from a data set. If you have an input, you can define it manually. Like you can say that these are kind of the stuff we take into account when we plan our path from one place to another. So if you want to drive a car, we need to know whether the road is drivable or not. You cannot drive right in front of the Memorial Union or the library, for example. So that path is out of bounds. Similarly, whether it's sunny or raining, if it's raining, I need to have an umbrella. Or I need to go by the roads which has greater shade. So all these are just an example which I have for today. For the same example, the agent user can have a car, can have an umbrella, can walk or can bike. And again, I have 2 rules which I'll show here. This rule, quite complicated to look at, but basically what it says is that if it's very sunny, as it's most of the time here, then you kind of try to find a path which has shades in it. So this is where we start with, that's the Brickyard building in red. And then we show that these goes to nodes 1 or 2. These are the 2 options at time step 1. Then because we're constrained by the fact that it needs to have shade, here we take this road we go from 2 to 3 and 6. And we don't go from 1 to 5, which is the Mill Avenue, and most of the time you can't walk down there because there's no shade. So I don't go into too much detail so that you can have questions, but basically that's how we see that it kind of tries to find all possible paths throughout. Now I go and say, hey, I give you an umbrella. So now you can go through places where you don't have shades as well. And then that kind of goes to, so if you look at the diffusion process, this kind of has more
or they did not update. Okay. Probably I need to show another figure, but later maybe. So lastly, this is something I'm already working on. A couple of you have spoken to. Yeah, just one more minute. Spoken to a couple of you about this. So this is a learning module. So the idea is that right now I'm defining that rule which I showed. But it would make more sense if I can come up with that rule like we do. That okay, like I will make my decision based on how sunny is it. And I take 1 week to, optimize after I come to AC, for example. So can we learn these clauses? And thing which I am following is the differential alpha work. There's some work on it, but not yet enough to show right now. But the idea is that can we learn these clauses and also the clause weights? So that's gonna be like why reason not learned. And the idea is that what can it do? So it can learn like human specified preferences, like I want to prefer a shady road, I want to drive, etc. Or it can also, like take in planned traces and learn the preferences from that without being explicitly mentioned. And lastly, this is something I have not started work on since it's open source, anyone's open to contribute. But given a course of action or a plan, can I evaluate the correctness in known environment and dynamics? And secondly, because it has explainability, like you can get back the rules from the trace, can I detect and debug logical errors for when there is an RL agent in connection? That was speedy, but I try to keep it in time. And I also finished with a big black thank you slide.
Go back. Go back. It's not, always improve yourself. Please never end with that. But if you do go to the thank you slide, then go back to the summary. So that people will remember.
Thank you.
Yes. Okay, thank you. So you guys can set up, and if there's a quick question for him. Is there a question for? Go ahead.
Yeah.
So you mentioned like that cases where.
Wait, is this yours?
Welcome, Sami. No.
Yeah, there we go.
Perfect.
Guys, other people should. Below.
Sometimes not as sometimes.
Yeah.
So in that case, we could take it as an input procedures.
Did I click it? Or I thought they were just using this thing to go through the slide. I see.
Yeah, it is already.
Fair enough.
Yeah. So in the report, you will also find a list of link to a drive link
Okay.
where you can
So
just
just
type
left
in
and right here.
the result. And the GitHub repo is already fully working, so anyone can try it out. Create your own virtual environment. The code is there, so please feel free to try it out. Thanks. Sorry for taking.
It's
That's good. All right.
Okay, next after them, who is going? Okay, Karthik and Devon. Then after that, you want to go. Okay. Okay, go ahead.
Cool.
So I'm Nicholas.
Okay, I'm sorry. So for the people who are have to leave at 4:30 because they have an exam, there are two options. One is they can take that sheet, watch the rest of it, and then write your comments on that too, and send us a scan. Or you can say we had enough in this course and let's leave this out. Either way is fine. Okay. That's it. All right.
So I'm Nicholas.
Go ahead.
Wait, will we wait for everybody to leave?
Yes.
Yeah.
It's too long.
It's good. It's good.
Okay.
Thank you.
Wait, is this your phone?
That's not mine. Mine's on the
Oh.
left.
Elsa, is this your phone?
Someone left their phone here, the front.
Someone's phone's here. It is? Oh, thanks.
Okay.
All right, I'm Nicholas.
I'm Harsha.
Speak louder, yeah.
And this is BB Player, a HMM strategy for blackjack. BB Player is short for Bender's Blackjack Player, which is based off of a famous TV show character that was a robot that was addicted to gambling.
From the drunk robot named Bender. He loves gambling and some other ephemeral stuff. But we decided to name a big player for one reason. We'll get to that in a sec.
So for the background, a game of blackjack is fairly simple. I'm gonna go over how it works real quick for those who don't know. So the player and the house, which is the dealer, draw cards until the hand value is 21, which is the maximum score, or they bust, which is when they go over 21. So when the player takes their turn, they're allowed to either do what's called a hit, which is where they draw a card and add it to their hand, and then their hand values be calculated, or they're allowed to stand, which is to pass their turn to the dealer when afterwards, which the dealer starts drawing their hand. So before the player's turn, they are given two cards. So they already start with two cards, and they're allowed to look at the dealer's first card, which is called the up card. And then they start making their decisions based off of the information of their own cards and the dealer's one card. Once they decide to stand, then the house starts drawing the cards until they hit a value of 17 or above, in which they stand, and then the person with a higher hand score ends up winning their hand. So the motivation for why we decided to study blackjack in particular is that the dex itself is unknown, so the domain is only partially observable. You don't know what card you're going to get before you draw. And the fact that in our case, we're going to work with decks that have highly randomized distribution. So we're trying to see whether our model can adjust to the fact that a deck may not be a standard deck of cards and such that it can learn the distribution and then start working with that instead. In comparison, we compared it to two major strategies, which was card counting, which is something that benefits from slight deviations from expected uniform distribution, in which they see what cards have been played already and look at the previous hands and look at what cards would be remaining in the deck, and then base their strategies based on what cards are remaining. In the cases where they've seen a lot of low cards drawn already, that means they understand that there's a lot of high cards in the deck, and such they will play less aggressively as they don't want to go over the cap of 21 points. In the opposite case, where they've seen a lot of high cards played already, they would play more aggressively because they understand there's a higher chance that they would draw a lower card. In our case, we decided to model the normalized card distribution and end up choosing the action, not the least risk, but the maximum possible gain. And we compared against that of many different card counting agents, and then also an agent that just took random actions, whether just to hit or to stand.
All right, so we're going to talk a little bit about the structure of BD Player. So right here for you, we have a small system diagram to make it a little bit easier to explain. So we decided to approach this entire system using the Turby learning. You might have heard of it in CSE574 or 4 but we're trying to learn the states and the true nature of our deck distribution using hidden markup models. Why do we choose HMMs in the first place? Well, it's a partially observable environment, and we don't want any control over state transitions. We want to learn them in the first place. So, yeah, we have 5 different portions in our system diagram. We have distribution update represented in pink, distribution filtering in yellow, the Turby learning in kind of, I guess, mustard green color, this is heuristic in sea green, and of course, decision making in orange. So initially, when we get into our system, we are starting the game. We have D in it, which is the first distribution, completely uniform. You have, I guess, 4 cards per value in your 50-card deck. And you kind of think that initially it's kind of being uniform, but we want to adjust it as we go through. So every time we see a card, we do a sort of smoothing to all the distribution. We add the card into the value that we pull, and we actually remove the card from the same middle ground range and remove another one from low and high, so on and so forth for the other 3 ranges. For distribution filtering, we actually apply a log normalizing filter to our initial distribution. We do this to sort of balance out and smoothen out the distribution that we expect to see, the possible distribution in the first place. And Turby learning, I'll be getting into in just a sec. Decision heuristics also the proportion that's very important to us, which has one slide. And that's also defined with decision making. So let's go on to the next slide, Nick.
Yeah.
So here's a behemoth of a network. That is the HMM that we use in Turby learning. So why does it really matter so much that we gave it an entire diagram? And yeah, it looks like PowerPoint swallowed some of the words. Google Slides didn't do that for us.
So I have three major portions of these HMM that I want to talk about. Our transition matrix is modeled by straight transitions. We have a layer of hidden transition states right below our initial state. Initial state is a string that we sample from this log normalized distribution. Now, for every single state in our hidden states, enumerated from ace to king, we have a red transition. That's what's shown right there, swooping up and swooping down. So we want to learn what likelihood it is to go from one state to another. Why do we use these states? When we sample a string from the distribution, you're guaranteed to have the true nature of the distribution in mind. We want to be able to learn how states appear with relative respect to one another, which is why we learn transition matrix. The emission matrix is specifically how from red states shown there, we can actually go to our end observable states shown in green. So if we can learn the T and E matrices and iteratively process this and normalize them, so on and so forth for about 10 iterations, we can actually converge the process to get a finalized observable string. This is actually going to be a true representation of the distribution as we know it. Now, layers, as I talked about, we have the initial, which is your sample string. We have the hidden layers, which are the hidden states, and we have our observable layer at the end. How do we just really use the Turby algorithm in the first place to even learn this, right? We actually backtrack from the observable states, find the path, the highest probability, go through all these loops with your hidden states, and finally we get back to our initial emitted state. The max probability roundabout. So here's our heuristic. Fancy numbers, right? So it's actually pretty simple. On the left-hand side of our heuristic, we have the true distance between, or not true distance, but the estimate of the distance between 21 and our current hand sum. We only care about our hand sum. We don't really care about whatever your opponent has. It's kind of a greedy approach in that way. So we do a summation of the values in your hand from the initial to the end. And then we multiply it by a log normalized smooth ratio of emitted states to transmitted states. We chose a specific ratio because we can actually model this entire distance as a true distance estimate of the number of cards you have to draw to actually get to 21 in the first place. On the top of our fraction there, the numerator, the left-hand side of the numerator represents the emission probability. We sum it across the emitted string, and we add a smoothing factor, which is the game state. It's very similar to add one or plus even smooth. We also use spread log underflow, common error when you're taking the log of anything. In the bottom, of course, is our transmitted state probability using your transmitted or observed string. So
let's talk about results for our project. We ended up getting our agent to have both the highest win likelihood and the highest final balance in terms of adding the betting into the equation. If you see at the top, that's that's our model, and then we have the random model, and then we have the 6 different card counting models that we end up using within our experiments. The ones that came closest were high, low, Zen, and halves, but in terms of just the final balance, the difference was pretty massive. I think also what was notable is that the fact that sorry, give me a second. So to get these results, we ran a batch of just blackjack strategies on 10 randomly drawn bias decks. So we randomly generate decks that aren't exactly the 4 of each card distribution you see in a normal 52 card deck, but rather ones that were just any variables. So some cards could be missing, some cards could have more there's more copies of cards. We didn't take into account suits because that wasn't necessary for blackjack usually. So in the end, with all of our tests, we ended up getting a pretty high successful win ratio. So we're pretty happy about that.
So a little bit really quick about our methodology. We randomly drew 10 decks from any number of initial decks. Normally blackjack, you draw 6 to 8, but we don't know how many we have. We have as many as a total of, I believe, 12 or 13 decks. We drew 10 of these, and for each of the decks, we performed 100 different games using randomly drawn 26 card shoes. So we try to induce some randomness into the scenario with that.
And then in conclusion, again, our model outperformed other blackjack strategies. In the future, we'd like to modify our approach to use informed transmission and emission initializations. In addition, we would also would want to think of specific like severely biased deck compositions in order to run our model in and see if we could recognize some extreme cases, like if there were only high cards existing in the deck or low cards, and would see if it would outperform the card counting strategies. Because in the case of the card counting strategies, a lot of these depend on understanding that the deck would have a normal distribution of cards, so they don't actually really successfully account for the fact that if there was like, say, like half of the deck were like tens, half the deck were aces or something like that, then we could see if our model would recognize that specific extreme circumstance.
Yeah, so along with that, we also have a paper up on overleaf on Piazza, but we already turned it in, I guess. We talk a little bit more about the entire system specification, why the heuristic actually matters, why emission transmission ratios should matter too, and also the initializations we use for emission transition, both randomized. We also have some experimental rationale along with why we specifically chose randomized decks, and a little bit more of a deeper look into the Turbine algorithm and why the Turbine learning actually matters for such a large network. And as well, we have open source repo on GitHub. There's a hyperlink if you want to click it, I guess. You don't need to click it.
Yeah, okay, over now.
Yeah, but yeah, we have everything there, full open source. Test it if you want. Yeah, RL could be kind of spotty, but we hope it works out. And that's all.
Cool. Yeah, and the next one can set up.
So I noticed if you go back a couple slides.
Sure.
All of the agents have positive win rates, including the random agent. So
Right.
what if the random agent is just randomly choose this hit or?
Yeah, so depending on the state, if it's initially, it chooses a hit, stand, or win, and then after that, it only chooses the stand.
This is something where we've had more time, we would have ran it on a lot more test cases.
I'm just curious, because I've done the impression that blackjack had a house advantage, so I'm wondering why the random agent has a win rate higher than.
I think when you take the health advantage, it's typically for the case where we have 6 to 8 decks only. So we have any n number of decks up to 12. So you can't actually get a true estimate of your true count without the number of decks.
Including the fact that the dealer has to follow like a specific strategy that wouldn't work with like the randomized decks that we've had, so.
Hope that helps.
Okay, thank you. And so after them, it
could be easier. Did you give a PDF or?
It's a PDF.
Oh, it's a PDF. Okay, let me check that. Yeah, it's exactly. Yeah, it is the one. Yeah, it's. Oh, this is the.
Okay.
You might-
Everybody maybe, yeah, right, okay, yeah. Go ahead.
Yeah, I don't think we do. We can do that. And it's this.
Okay. So. Yeah, ours is called, I mean, on the sheet, it's called, solving MDPs with IPs. That's actually a typo. It was supposed to be solving MDPs with LPs, linear programs. And, that's been done a few hundred times before. So we're specifically talking about a class of MDPs called constrained MDPs. Ignore the probabilistic temporal planning because we don't have time to get into that. Okay, so we're just gonna talk about like the problem. We're gonna do a bit of state setting, and we're going to talk about how to convert our constrained MDP, which we'll define shortly, to an LP, and then we'll describe why the LP sucks. Okay, yeah. Okay, so in the paper we like spin this in terms of probabilistic temporal planning, but like any good mathematician, we're gonna ignore all motivation, talk about the problem on its own. So an MDP is, I mean, we're all familiar with it, just a
a collection of states, actions, and transition probabilities, and you get a reward for taking an action in a state, right? It's a function on your state and action. An MVP that returns multiple rewards. There's a couple of things you can do with them. One of which is, multi-objective MVPs, where you just take a convex combination of possible rewards that you receive. Another thing that you can do is constraining the solution of your MVP. So, for example, and in our case, your MVP returns 2 rewards. You want to minimize one such that the other reward is above some threshold, right? And this could result in different solutions than if you didn't have this second constraint on top. Now, I think it's a very old and very well-known result that you can turn an MVP into a linear program. As a matter of fact, we kind of stole the normal linear program from Luderman's book. And it's easy to add constraints to linear programs. CMVPs are something that you can constrain. I think CMVPs you can't really approach with dynamic programming as easily. I could be wrong about that. Yeah. So the constraint that we're having is specifically time. We're treating time as a second cost, and we want the expected time of a policy from the goal state from the initial state to the goal state to be below some threshold, which we're just going to call a deadline. And I mean, the key insight here is that time we can just view as another cost. This is the constraint that we have, and it's actually surprisingly difficult because expectation is nonlinear. There's a trick that we can do to approximate this with something that we're going to call occupation measures. But yeah, the original LP for an MVP looks like this. So this right here is basically just the Bellman equation. U of S is equal to the reward plus this greater than equal to sign just means that you're maximizing thing on the left, but it just means U of S, the utility at any state is the reward plus the discount factor times PSAS times the utility of the next state. This we've all seen, and for all goal states, the utility is just the reward. Because goal states don't have a future. You want to minimize the utility. That alpha is just some collection of arbitrary constants. Don't need to care about that. And we can add constraints to this. This is the one that is given in Kluderman's book. So the way that we add constraints is by defining 2 measures, a positive occupation measure and a negative occupation measure. The positive occupation measure is the amount of time it takes for us to reach the goal state from a given state, right? Our estimate of getting to the goal state from our current state. And the negative occupation measure is our estimate of having already reached the state. Now, we're always optimistic with our future states, and we're always pessimistic with our past, right? So we assume we've taken the worst possible time to get to the state, but we also assume that we're going to get to the goal state in the best possible time. And these 2 occupation measures must sum up to some deadline T. And this is where the utilities come in. They must be less than D by default, but we can treat the utilities as a slack of some kind. And surprisingly, this sort of works. The justification is given in our report. And we can convert this into the LP, which is going to be on the next slide, and it is a bit of a mess. Godspeed explaining that.
So essentially,
He gave you the easier thing.
we're taking the original MVP and we're adding all of these new constraints. So we've added the occupation measures, the positive and the negative. But in this instance, we're treating them very similar to how we treat utility values by ensuring that the positive occupation measure is maximized and the negative activation measure is minimized to do so. In doing so, we essentially cause the time to go to be minimized and time left to be maximized, as we mentioned. And then as in the previous slide, we have the basically the equation for this having the slack variable of the utility. And then we also have for the initial state, the time to go should always be less than or equal to the deadline itself, because we don't want to end up going too far past the deadline in terms of the time and the amount of time we've actually been spending towards the goal is obviously going to be greater than or equal to 0. It shouldn't be any less than that. And then we've just got some basic variables at the bottom there for the occupational emergency should be greater than or equal to 0 for all of the states. And all this is for all the states and for the actions for the occupation measures. To actually implement this LP to determine whether or not it was functioning and whether we could actually solve a very simple problem, we implemented it using a free open source software called Hope, which is basically an LP solver. And we found that the LP was actually infeasible according to the software, even though the problem we know is not feasible. We believe that there are a few problems with the construction that likely could be fixed, given more time on the project. The largest one that we found was that the probabilities for the negative occupation measure, we used essentially the wrong probabilities, because obviously due to Bayes theorem, we should be using Bayes theorem to determine the probabilities of every state that the agent could have come from. So the probabilities that we ended up using did not sum to 1 like they should have, and normalizing this and using Bayes theorem would obviously fix that. We also can't really use the utilities as slack without more than scaling, because it just wouldn't be linear with the way that we've set it up. We probably need a quadratic program in order to do that, and we need to find a way to avoid that in order to ensure feasibility.
Yeah, because the whole point was making sure that our entire thing was polynomial, and if we were to do a quadratic programming is NP complete, and that would decidedly not be a polynomial time solution. Yeah.
And so here are some of the outputs from the actual program that we ran. So we first created a simple program to run value iteration and showed all the values for this particular instance, the simple 11 state instance. And then we also solved it with the unconstrained LP to make sure that the values were the same between the two as how they are. Yeah, and then this is the actual LP, as it tells a lot of stuff there, but we've got the utilities and the positive and negative occupation measures on the right. As you can tell, the values between the two are still correct. So that means that basically the LP did end up solving it very similar to value iteration, but without considering the deadlines essentially. And we've all, as you can see, a lot of the negative occupation measures are 0, and we believe that the reason for that is the way that we set our LP response, and we wanted to really fix that.
Just as clarification, this is the blocks world domain from Russell and Norvig, the 4x3 blocks world with the 2 goals in the corner and the initial state in the bottom left corner.
The maze, not the blocks world.
That's okay. Yeah, and I think like with a little bit of extra work, we fairly certain that the occupation the split occupation measures idea works. We haven't been able to prove any we haven't been able to show that the expected value of the initial to goal state is actually produced by this LP. I kind of suspect that it is, but again, I haven't been able to prove it. It would have been a nice group to include. And we don't have a thank you slide, so. Yeah.
You didn't expect any questions.
Okay, go ahead.
Non-technical, on a scale of 1 to 10, how much does your head hurt?
12. Yeah, this is a little bit dense. This was a very theoretical project. We spent like a month coming up with the LP, and unfortunately, like there were a lot of ideas that we ended up trying that just ended up not working, including this one, which also doesn't work. So yeah, I really wish that like we had, I really wish that like that second LP just showed some degree of partial results and would have showed that the deadline is possible, but unfortunately it ends up being infeasible all the time. Yeah, we again, it's because of the fact that we're not weighing our probabilities correctly for the negative occupation measures. Yeah. There's also this gigantic and frankly awfully written monograph that is very notation heavy by this French mathematician that talks heavily about constrained MDPs. And yeah, transcribing that notation into something more reasonable, something that looked like the Russell and Norvig notation was a pain. Yeah. Okay.
Not a question. I actually have read the paper.
Okay.
I've read it. It's actually really like cool. I recommend actually reading this one.
Okay.
Go do that.
Okay, so any other question? So basically, when you say constraint MDP, what you're doing is you're taking a multi-objective MDP and making one of the objectives like requirement. Like, you know, if you have a travel plan with, you know, where you're trying to optimize both for time and cost. Instead, you are saying, give me the shortest travel plans subject to $500 being the
most you can spend on it. Yeah, correct. Actually, it's the other way around. Give me the cheapest plan that subject to me getting there in.
Whichever, I mean.
Yeah.
I mean, you could switch them around.
No, but it's not very clear to me that the time aspect is important. It's just.
It's not. I mean, we kind of just say that we're calling time a second reward. The important thing here is that the reason that we're using time is that the expected value. So for any policy, the expected value of the time should be less than the deadline instead of just the time being less than the deadline. It's the expected value because again, it's probabilistic. So that ends up being very messy because again, expectations non-linear and we're trying to shove that into a linear program. Yeah.
Okay, now thank you. So then after that, Sean, after that, Luca, then Sean, and then who else? And then and then who else is there?
Wait, what's going on?
Oh, I think it's just up there.
Yeah.
Oh, you got it. Okay. Is it just down?
Yeah, it's just down.
Okay.
Yeah.
Okay.
All right, so hi, everyone. I'm Matt and this is Dennis. And so you'll notice we exchanged our long name for equally long name. But and the reason behind that was that we actually we still are attempting to do that long name, but this was actually kind of a precursor work to getting towards that. So essentially what we're doing in this problem is that we're taking a look at so with symbolic, when you attempt to apply symbolic subgoals in like low level domains, there's often many different ways that you can do that. And we're curious to see how this works in continuous spaces, in particular in this one, a three-dimensional Isaac-Jim space. So I'll talk a little bit about, yeah, so the background for this actually was from the Leveraging Approximate Symbolic Models paper, and which we actually heard a little bit about last week. So in short, with this paper, it looks at the it kind of builds the motivation for finding a couple of diverse low-level ways for
exploring those symbolic subgoals. If you want to move on to the next. So more or less these subgoal serializability problem. So what we were curious about in this paper is specifically when those subgoals aren't in a kind of compatible or easily to exchange format. So for example, like Dennis will go into a more concrete example, but when we want to basically describe in a symbolic setting, like maybe the plan that you would take, but then our actual low-level state space is in terms of coordinates. It's we wanted to kind of explore how imposing like reward functions as these subgoals would work. So kind of one of the problems you might run into is that achieving a subgoal, if it's like simply specified, you may end up meeting the target for that subgoal, but you may end up in a corner, either literally or figuratively, and you can't go on to actually achieve those next subgoals, next symbolic subgoals, even though you did what you were told to do, basically. So our project, like I said, is working in a continuous three-dimensional domain on this.
Yeah, so here's a pretty simple example of what Matthew was just talking about. So we have a plan, it's go to the table, or we have like the human incomplete thing or whatever. And the human says, okay, you should go to the table, you should pick up this duster, even though it's a broom, you should go to the window and you should dust the window. But if we look at the plan here, the robot goes over to the table, it picks up the duster broom, and then it goes over here and it can't dust the window because it's holding it incorrectly, right? So really the thing is, like, if it had been on the other side of this table, it would have been able to dust the window properly. So sort of the thing that we're focusing on in this project is this first scenario. So basically we just show in Isaac Gym that the positioning of the robot with the table matters, and it could cause, even if you complete the goal, which is to pick up the broom, you might not be able to achieve the long horizon goal, which is to do stuff with this window. So here's what Isaac Gym looks like. This is our simulation setup. We have a pretty basic setup. Basically, it's just the Franco robot, table, and it's a broom. Really, the only complexity in this was the broom, because we had to import a 3D model for the broom and transform it into a URDF file. And because of the limitations of Isaac Gym, we couldn't find the closest distance to the broom easily. So what we did was we inserted two invisible joints, one here and one here, and we used that to calculate the reward function, because we were able to just get the points where the invisible joints are, and then we could use that to find the closest distance with just some calc theory.
All right. So a little bit more about our environment. So we actually have, so our agent, which is this Franco robot, has we actually use two different modes of action. So this was inspired by someone done at CMU that also dealt with Isaac Gym, but one mode is joint mode, and this is where the action space for the agent is moving each joint individually. So for Franco, this is 9 different joints. And your observations are joint positions. The other mode is a tractor mode, and this basically kind of abstracts away the joints, but still gives you the flexibility of working in the 3D space. So you basically your action space is small little trajectories within the 3D space, and the observation is of the hand specifically, and the observation is the hand's location in space. And so this actually uses Isaac Gym. Isaac Gym has logic under the hood for calculating those what joint spaces are necessary to achieve those results, but still using this mode doesn't actually, despite the fact that it abstracts things away, it still gives the flexibility of the continuous space. For our reward function, because we're trying to look at proximity to the broom itself, we are just looking at change in distance, change in shortest distance to the broom. So any changes in the point on the broom closest to the hand. So we are going to incentivize things that actions that move closer to the broom and penalize actions that move away from the broom. And then for our terminal state,
we set an epsilon distance from the broom, and when the agent achieves that, it completes. Otherwise, we out of time, 120 time step limit. Yeah, so you can see our army of Frankas here, as we call it. But basically, we one of the big parts of this project was developing this abstract wrapper for Isaac Gym. And so this wrapper allows kind of OpenAI style environments to be defined for Isaac Gym, and allows easily kind of customizing those environments. One other interesting note on this is that we actually are able to reuse the agents in new environments. So say you want to like have Franca do some other things or work with maybe like 5 different tables instead of just one. You can reuse the Franca. We've pulled out Franca and its action space, and that can easily be applied in new environments. And this will also, and key here is allows easy customization of reward functions too with that. So for future work that we want to pursue, we'll be able to kind of encode other symbolic sub goals very easily. And one cool thing about Isaac Gym is this vectorization. So we create multiple of these like identical environments in parallel, and we can use stable baseline 3's vectorized API to help with learning.
Yeah, so our results are pretty simple. So we just put a robot on the left and a robot on the right, and pretty clearly the robots try to take the shortest path. So what that means is it kind of enforces our idea that if the robot is told to go near the table, the location of where that robot goes will matter, because if it goes over here, obviously it's gonna pick somewhere close to the bristles of the broom, and it won't be able to successfully, say, clean something high up. Whereas if it held it over here, it would be able to do that. Yeah, so we have some videos. They're really slow. Okay, I guess.
I don't know if they actually click, but
Well, just know that they touched the brain.
they're,
So these were real-time videos.
yes, these were recordings of the like a playthrough of
Yeah,
the.
you know, the usual thing is they will show it fast and will say 50,000x speed.
Oh, yeah,
If people actually saw any of these things in real time, there's no like time left.
yeah.
Reinforcement is extremely. slow.
Yeah, be glad you're not actually watching
Yeah.
this, guys.
No, you should just make versions of it with this 50x, whatever,
Okay,
10 million X speed, so that it's like 4 seconds.
okay,
Everybody done.
sounds good.
Okay, let's
I don't, okay. Did I go the wrong way? Okay, cool.
Yeah, so basically our future work is to try to incorporate pre-trained large models or PLMs to improve the agent's ability to find serializable subgoals. And how we plan to do that is we plan to use image models like Stable Diffusion, or just use like things like Google Images to generate some images. And then we're going to try to sample those images and convert those into low-level space to use as subgoals. So for the problem that we encountered, maybe one of the image we would sample would be like, okay, the robot needs to be on the far side of the table or whatever. And that would hopefully allow us to tackle the intractability problem that the diversity objective in Lynn's original paper, which Matthew talked about in the beginning. Hopefully it'll help us address that and allow us to use that sort of framework that Lynn introduced. We have a credit slide. Thanks, Lynn, Professor Rao, for teaching the class, and then we have our report.
Everybody else before this, the rest of you should quickly change your slide.
And there's an extra bullet, but basically our report goes more into detail about what we did, obviously, and then in addition to what wasn't presented, we have some detailed explanations of code and movement modes. We also have more results, so we showed what algorithms we used and how they performed on the simple task of just touching the broom. And we also have references. And that's it.
Your time for questions here.
So you experiment with different single gathering distributions to improve.
What?
Did you throw it like some different center of gravity distributions?
No, we didn't really mess with the broom that much. Really, the only thing we did with the broom was created, turn it into a URDF file, which honestly was a lot of work, and placing the balls inside of the handle was extremely painful and took many hours because the broom was rotated in a way where the XYZ axes were like tilted. So I couldn't really figure out what was going on when I was changing values. So because of that, I didn't really focus on any of the physics parameters of the broom.
And for this project, like we focused mainly on getting to the broom, so like picking up the broom was not as crucial, but I imagine that like, you know, that could be a huge impact with the feasibility of some previous states going forward if that, you know, the weight distribution of the broom actually were to change.
Cool, thanks.
Okay, thank you. Next. Okay, with us. And then Sean, and then Upasana, and then you're the last. So you're big prize. Nobody will know.
It's a PDF file.
Is it the one?
Yeah.
I think you can.
Yeah, perfect. Okay, can you hear me? Basically, yeah. My name is Lucas. I'm going to be presenting inducing neurosymbolic world models. It's the second project on the back page. So in the class, we've discussed a lot of different world models. For the most part, we focused on discrete symbolic world models, but most naturally occurring models have a mix of both continuous and symbolic structure. So we covered this one paper, planning from pixels, right? It focuses on control tasks that are primarily continuous. But obviously there are plenty of tasks that are fully discrete. I would argue that, you know, most models are a mixture of both continuous and discrete components. And furthermore, like all world models are going to be abstractions. So even if the environment is fully continuous, our representation of it still might leave out certain details that aren't important. And so the question I'd like to address in this project is basically what level of abstraction is appropriate when an agent is learning a world model? And furthermore, how do we establish the boundary between a symbolic and a sub-symbolic component of a learned world model? And I'm basically proposing an algorithm that does this. So here's like an overview of this algorithm, which I'll explain in technical detail next. But the core idea, right, is to learn a neural model for sub-symbolic continuous dynamics, and then use this as a starting point to learn a symbolic PDDL model that describes things that are best described symbolically. And so we can condition these two models off of each other in a technique known as anchoring. And then through environment interaction, we can build up a better symbolic model. And so I'll go over basically the technical aspects of this. So the first proposal is basically to treat PDDL models like program trees. So we can parse PDDL. It's basically just Lisp code. And this lets us define interesting operations like isomorphism and edit distance. This is related to Sarath's work, basically on like world model similarity and minimally complete explanations. Next, we basically define, we use algorithmic information theory to describe the information content of a symbolic world model, and also to speak about different specification languages. So PDDL is one language, but we'd like to reason about different languages and vocabularies that you can choose for a symbolic model. And we're going to use this technique to establish the boundary between symbolic and sub-symbolic models. And then those two preliminary parts are going to lead to the actual induction algorithm, which, like I said, is based on anchoring, where we first learn the neural part and then we learn a symbolic part afterwards. And yeah, so I'll just start by describing, how we can see PDDL as a program tree. So essentially, all the domains we've covered in like our homeworks for this class, we can describe in terms of predicates and actions. And when you parse this, right, it just becomes a tree. And we can model this, as vertices and edges.
And importantly, we can define basically the equality of different trees through isomorphism, and we can reason about the differences between two models in terms of edit distance. Also, trees are these discrete objects, so we can actually search for a particular tree that describes a world model. Yeah. And so this is the first idea, is that basically we can reason about whether two world models are equal in terms of if I can rename concepts in my world model to match concepts in your world model. So if you and I have different names for walking, right, we might actually still have the same world model as long as we can find this transformation between our models. So formally, we can think of that as an isomorphism where we have a bijection between the two trees. In the cases where like a simple transformation is impossible, we can instead reason about this through edit distance. So luckily, both isomorphism and edit distance are well defined for trees, and they only take polynomial time. And what we want basically is the edit distance to a tree that is the same world model that another agent has. And we can use that to provide explanations, but also to find world models that match data or traces. So here's just an example spelling out what that looks like. If I have a world model in the logistics domain, and it is missing a particular predicate, I can express that through edit distance, highlighted in red. And then similarly, I can just rename components to match someone else's model. So that's how we describe world models as trees. The next thing is how we describe the information complexity of a model. So algorithmic information complexity is this idea that the information content of an object is the length of its shortest description. And similarly, since we have a quality of model trees, we can define the information content of a PDDL model as the length or the size of its minimal tree. And so basically, we're going to use this to reason about the information content of PDDL models, and also to search for them. Furthermore, if I have two different PDDL models, or sorry, two different models that are expressed in different languages, like one is expressed in PDDL and another is expressed in a variant of PDDL, I can actually, if I can convert between these two languages, the information between the two will differ by at most a constant. And this constant is interesting because it allows reasoning about communication, because it captures basically how similar two different languages or vocabularies are. And it also, I think, might capture how easy or natural it is to express a world model in a particular language. And in this way, we can maybe use it to establish which models are best used for symbols and which are best sub-symbolic. So we can formulate our objective for the algorithm using this. So stated intuitively, the objective is to learn a world model and then learn a split between a neural component and a symbolic component so that overall the information is minimized. So we find the minimal model that basically compresses our experience, and we want to split between expressing things neurally and expressing things symbolically. So for instance, because it's difficult to express how we walk, we'll express that basically with a neural estimate. And then, we can still describe symbolic aspects of walking, like turning left or right, and that will be expressed via the symbolic aspect. And so this is a high-level objective that can motivate like a more realistic optimization objective. And we can search for these world models and a split using some kind of discrete algorithm. So this is overall what the proposed algorithm would look like. So in the middle, right, we have our neural model and our symbolic model. The neural model is actually this recurrent state space machine from the Planning from Pixels paper. And it's basically predicting the next state in latent space, which is like this compressed but inscrutable representation of continuous dynamics. And then the proposed PDDL model learns from this and builds symbolic PDDL describing the symbolic components of the algorithm. And once an agent has these two models, it can formulate like exploration goals as to like what it needs to fill in. So if there's an action in a model, like say, the walk action or something, if an agent tries to go through and unlock like a door that's locked, say, it might not know how to reason about things that are locked or unlocked. And so that might become an exploration goal that it forms to explore in the environment and build up a better world model. And then once exploration is done, right, it receives model traces and tries to induce new world models using basically the preference learning methods that we described. So that's kind of like the ambitious proposed algorithm. And there's a lot of directions that it could take. So if you go look at my paper, you can see basically a literature review and summary of what led up to this, more details on the math formulation, and pseudocode for the proposed algorithm. So after this, I hope to do a full evaluation. I've implemented some of the components. And then actually my main goal is to compare for different objectives, like for compression, communication, reward, or predictive coding, what kind of world models we actually end up with through learning. And ideally, we want to find out which one of these objectives aligns to learning human models, like that are expressed in the human vocabulary. Because it's not obvious that a communication objective, or sorry, that a compression objective would lead to human vocabulary symbols, but maybe communication or some other objective could lead to human symbols. And then finally, I want to mathematically formulate the curiosity aspect of this, and turn this into a complete world model induction algorithm. And then yeah, I'll go back to this slide, but I'll take questions.
Questions? Yes, correct.
That's in Beaver, right?
I couldn't hear that.
So your slides are in Beaver, right?
Yeah.
Okay, can you send me the template?
Yeah, it's somewhere on a really minimalistic template or something. Yeah.
So, my question is with regards to the distance metrics that you have talked about
Yeah.
between the two different abstracted world models, and in fact, even when the language differs, is like very straightforward question. Was this part of your formalism, or is there any other related ideas? Or
well, it's totally based on Surratt's formalism, where so Surratt's paper is basically this idea that you can like form a lattice of different models, like where you take and add predicates. It's the same idea, except that you can add subtrees or like any of these tree operations. Like so adding predicates is like a special case then. I mean, it's kind of like, I'm not totally sure whether it would work, but that's the formulation I came up with.
When you said that there is you're computing some information content and then overall minimizing it, that's what the equation was. So
Yeah.
I got the symbolic part of it, but how are you computing information
Yeah.
for the neural?
Yeah, that's a really good question. And actually, it's not obvious that you can directly compute the information content of the neural component. And instead, you would use some kind of proxy objective to that. Like just the prediction objective, like predictive coding. You could maybe use that as a proxy to finding a minimal model. I mean, what would really happen is you would specify like some fixed network architecture and then train that. But we can at least reason about the symbolic information. Yeah. Does that answer your question?
So that's part of your objective, so you need to calculate.
Yeah, it's like it's a motivating objective more than like something you literally calculate. Because you can't like you can see like view neural networks as like compression, but we're not literally changing the size of the network. So unless we try different sizes of network, we wouldn't literally be calculating the algorithmic complexity of it. You could do that, but it's not actually what I'm proposing. Yeah.
Okay, thank you. And while Sean is setting up, two things. One is, so long time, who was the professor in that class, just assume that final exam will be in the same classroom as the normal class. And
This one, right? Yeah, this one.
and so he was very confidently telling me that. So he told his students too. In a way, we could have done anything different because those guys actually are taking timed exams and you are giving things, and so I have to let them go, but we were completely, we actually owned that room, you know, but we just gave it up, so.
Okay, so my name's Sean, and I'll be presenting particle swarm optimization as applied to the multi-agent pathfinding problem. I've got a timer going here, so I'll try and keep it fast. I'm not sure we still, I'm gonna keep it in, okay. So my motivation for this project is that I'm really into bio-inspired algorithms. Those of you who may have taken Dr. Pavlik's course, CSE598 on bio-inspired optimization, may have heard of particle swarm optimization before. So the idea is, obviously we all know about path planning. I'm not going to talk about it too much. We've all had some experience in 571 about path planning. But basically the goal is to construct a path from start to end. And in general, usually you want to optimize some criteria such as path length or energy consumption, something like that. Particle swarm optimization, on the other hand, is a general optimization algorithm that can be applied to a whole slew of different problems. It's a population-based method that basically takes inspiration from, as its name suggests, swarms and flocks of animals in nature, so like a school of fish or a flock of birds. So I hope to tell you all about how I implemented PSO from scratch for path planning and demonstrate how it works for multi-agent path planning. So I already said that first part, but basically in this formulation, the particle, which forms part of the population, the swarm, is basically just a local search point in a sensor range of an autonomous agent, a robot in this case. The search space that I used was the MapF benchmark. They have a whole bunch of maps and scenarios for multi-agent path planning, and I just chose a subset of those of varying sizes and complexities of the maps and scenarios to evaluate my implementation. So as far as how PSO works, basically, as I already said, the swarm is made up of these particles. Each particle generally represents a potential solution to a given problem. So again, this could be used to optimize a lot of things, but generally it's good for continuous nonlinear functions. You can see here that there's an inertia weight. So that controls how much the previous step velocity influences current velocity. There's a cognitive parameter, which basically says, okay, how much do I care about my own, if I'm a particle, my own personal best? And then the social component, which is how much am I following the group and am I going after the global best that's been discovered? So depending on how you choose these parameters, the C1, C2, and W, that'll influence the overall group dynamics that emerge from the PSO algorithm. So yeah, during each iteration of the PSO algorithm, this velocity is calculated and the particles update their position based on their present velocity. So to apply this to path planning problem, it's really simple, actually. We just want to minimize this accumulated Euclidean distance. So what we have here is the sum of the distance from the particle to the robot and the particle to the goal. So the idea is that you don't want to just let the particle run wild and go towards the goal. You also want it to sort of find a reasonable midpoint in between the robot's current position and where it's trying to get to. So here's a little visual of how this would look. This is a very simple mock-up that I put together. So the particles are initialized randomly in the search space. This R is the robot. And this sort of white box represents its sensor range, right? So we'll initialize a handful of particles in this space and then run PSO for a few iterations. And then when it's done, it might look something like that on the right. So in this case, we would assume if we got a result like this, that our goal was somewhere off to the lower right. So based on this result, the robot takes a step and then it basically repeats the PSO sensing operation. So this right here is enough to solve the path planning problem with PSO. This works just fine. The authors that I based this work on, they said this works great. They have some additional details on obstacle avoidance, and they said it works great.
in practice, I found this doesn't work so great as soon as the obstacles are a little more complex. So they had this nice environment with few round obstacles and it could just find its way around. But if we have an environment like this, this comes from the MapF benchmark, we have a problem, right? So assuming we're trying to get, like, for example, from the top left to the bottom right, you see that we have all these local minima, right? All these dead ends that we could get caught in, all these little corners. And this whole thing breaks down, right? So how are we going to deal with these local minima? So one approach is to select randomly a perpendicular subgoal. So let's say we're trying to get from, again, top left to bottom right, and we get caught in this first corner here, let's say. So if we randomly select a subgoal, it might be one of those two endpoints there, right? Now, the problem I had with this approach, even though, again, the authors say this solves it, is that, what happens if we choose this subgoal? There's no way for our robot to make progress. If we choose this subgoal even, there's no way for a robot to make progress without first going away from the subgoal to get around this corner. So again, there's a problem here. And unfortunately, the authors of this paper didn't share their code, and they didn't share their hyperparameters either used for the PSO algorithm. So like the number of particles, velocity, inertial weight, that's those sorts of parameters that I briefly touched on before. Just checking on my time. And so I was not able to basically adapt the PSO algorithm to this maze, but I wanted it to work in a maze. So I decided, let's just make it do a local search for the subgoal. So I used just like an A* search for when it's trapped with no possible way out. And I ended up with a PSO algorithm that does work on the selected subset of MapF benchmarks that I had. Overall, although I'm able to make the PSO algorithm get to the end, the results were a little bit disappointing, as it turns out. With the MapF benchmark scenarios, you basically introduce a new agent, and then you try and plan and plan and plan until you run out of time or memory, whatever your chosen constraint is. And so generally, I found that for very small environments with no obstacles or few obstacles, I could get 4 or 5 agents to plan to their destination within the time limit. But beyond that, it really kind of broke down. And the reason mainly was that I implemented all this stuff from scratch, and the collision detection was very inefficient and time consuming. So I have a future work slide coming up next where I'll talk about that a little more. But basically, as the map grows and the number of obstacles grow, this sort of takes a nosedive in terms of performance. So as far as future work, I would like to implement the vectorized version of PSO, which, as its name suggests, uses vectorized operations to try and, well, it does eliminate some of the for loops present in the PSO algorithm and cuts down on the complexity that way. Some authors have used better collision detection methods by building on a platform like Unity, which is a little more purpose-built for that sort of thing. And then also, as I mentioned, the hyperparameter tuning. So all of these hyperparameters, like the cognitive and social factors and inertial weight, will have an effect on the outcome. And it's not clear without just running it if they'll help or not, basically. The main thing, though, also is that it's kind of unfair what I put the robot through, because it has a constant speed limit. So of course, as the size of the space grows, it's going to do worse and worse, and it's not going to be able to plan as well. So adapting the speed limit and sensing distance to the domain size is another possible way I would like to look into this. So in my report, you'll find a more in-depth discussion of the PSO algorithm and the versions of the PSO implementation for path planning that it's based on, as well as the full source code repository is linked there, and the results I gathered on the MapF subset that I had selected. So that is all I have. The next thing I have is a references slide, so I can show that or not show that. But yeah, please, any questions you guys have. I've tried to keep it really brief so we could
do 20 seconds of questions. Yeah.
I just have a quick question for clarification. Is the point of particle swarm optimization to make the particles move organically, like a swarm of bugs?
Yeah, so it's based on like flocking birds, right? So they kind of sometimes you want to maintain like a distance between them, but also have them explore the search space. So if I go back here a little bit to this one, you know, like again, assuming our goal is down here to the right somewhere, this particle on the top left would get a strong motivation basically to move down to the right. And in fact, all of them would sort of gravitate towards that direction. In this case, there's no, there's nothing keeping the particles from colliding into each other or anything like that. It's not really important. The main thing is just after you run the PSO, you want to get that best value. And then basically what I'm doing is constructing an array out from there and saying that's the direction we need to be moving the robot in. So, yeah.
And those particles communicate information to each other.
Yeah, it's so on that level, they're all aware of each other, of their own best experience and the global best experience of the swarm. Yeah.
So they're aware of the entire system, not just like the neighborhood.
Right. Yeah. You have a question?
Oh, I was just gonna say, one of the really cool applications that they can.
Yeah. Yeah, I thought it was cool. I thought it was an interesting algorithm, and I wanted to see if it could be applied to path planning. And I was happy that I got an algorithm out of it that could solve the problem. But again, there's definitely some efficiency improvements that could be made to get more agents solving the problem.
Thank you. Oh, you have. Can you possibly specialize particles then into different, like, once they're aware of each other, you can specialize particles to be different parts of that line?
Well, so there's so many different ways PSO has been applied to the problem. So like there's one formulation where the particles are paths. And so you're actually just having the paths compete in terms of like smoothness or path length or something like that. And so, yeah, there's different ways you can go about it. Specializing the particles, the whole idea is that they all work the same, right? So, yeah.
Yeah, this thing comes from the birds swarms and that's the. Yeah, thank you. Okay.
You have two of them. Which one is it the final?
Final, sorry.
Yeah.
Was me.
How did Lucas come? Yeah.
Hi, I'm Upasna, and I am here to present my type 1 project comparing AI versus human suboptimality for cooperative gameplay. So the motivation, I am personally very interested in human-robot interaction, and that's why the focus is on specifically cooperative multiplayer games where the agent has to cooperate with the human to get a common objective. So I wanted to see in such a cooperative environment how the AI learns as compared to how we as humans learn. So firstly, how do reinforcement learning agents learn to play multiplayer games? So a multiplayer game can basically be treated as a multi-agent learning environment. Classical reinforcement learning techniques are designed towards single agent learning environments. So when you introduce more agents into the environment of this agent, then the issue that happens is that the agent's policy now also depends on the behaviors of the other agents. Therefore, the environment now is not stationary anymore. And a stationary environment is essential for convergence of most RL algorithms. So how does self-play solve this? So self-play, what it does is basically it reduces the multi-agent problem to a single agent learning problem. So the policies of the other agents during the policy update state is fixed as the last policy of the agent. So in doing so, the environment is now stationary, and it develops new strategies to learn against to play against older versions of itself. So now, what happens when we apply self-play algorithms to cooperative games? So this is the game. It's basically extended grid world. It's called Overcooked. So in this, the objective is basically to cook soup and serve it at the serving station. So these are the onion dispensers, and you have to pick onions from here and drop them to the pot, and then it waits for 20 time steps while it cooks, and then you have to pick the dish up and serve the soup at the serving station. So so basically both the agents have to work together to get the common reward. So here we can see there are two strategies which could be used in this scenario. In the first strategy, each of the agents is acting individually and there is no interdependence between them. And in the second strategy, there's you can see there's coordination and it's faster because they're passing the onions on the counter between them. So this is a faster strategy, but the issue is that both the teammates need to be aware that this is the strategy they are following. So there needs, and this is where self-play faces issues when coming to the complexities of coordination, is because for coordination, the strategies of both the teammates should align. And when playing a game, how do we form strategy? It depends on our model of the teammate, right? So what happens is, because self-play doesn't encounter any humans during its training and it only learns by playing against AI agents, it is not able to estimate a good model of the human. And there is because of this difference in the actual humans model and the estimated model, coordination performance of self-play agents turns out to be really poor. So now the question is, how in cooperative gameplay, how can the agent accurately estimate the model of the human? So for this particular for overcooked domain, these are some of the state-of-the-art methods. So first is behavioral cloning, in which basically they collect human gameplay data, and then they use behavioral cloning to form a model of the human, and then the agent learns to play the game by training with the human. The partner agent is the human model. So this is a good approach, but obvious glaring issues is that collecting human data is not easy. It's a pretty expensive process. And also behavioral cloning is generally not able to capture all the complexities and intricacies of human gameplay. So the next approach, which is fictitious co-play. So in this, they use so if you think about it, why is it so difficult for an agent to play with a human? It's because humans have diversity. There is diversity in knowledge, there is diversity in abilities, there is diversity in intent, which is why it is so difficult for an agent to understand what kind of human there is in front of me. So this work uses the insight that diversity, if we provide diverse conditions during training, this can help us in training agents which are capable of actually collaborating with humans. So this diversity, the main focus of providing diversity is basically in skill level. So they basically implement a pool of diverse agents, and each of this, so how do we get these diverse agents? So they use self-play to train an agent, and during the training process, they take checkpoints. So checkpoints during the training process, and each checkpoint is treated as a skill level. So and then these differently skilled agents are the training partner agents for the agent. And then if the agent is trained to give the best response, to a variety of strategies as well as skill levels. But the assumption which this work does is that AI suboptimalities are similar to human suboptimalities. And if we consider all level of skilled AI agents, we are also capturing skill levels of human agents. So I wanted to investigate this particular assumption in detail. So similar to their approach, I developed a pool of diverse agents on these three layouts. So these layouts, the first two layouts present mostly low-level motion coordination challenges, and this layout, presents more of like high-level strategy challenges, is like how to do the task on a higher level. So more details about the method I've provided in the report. So after this, to evaluate how this diverse pool of agents is able to play with actual humans, I conducted a user study. I recruited participants from Amazon Third, and because a lot of people obviously have not heard of this game, so instructions, we also have the tutorial before so that they can understand how to play the game. So coming to the results, so this was supposed to be a video, but I'll just explain. Coming to the results, qualitative results first. So in the agents, one of the two biggest suboptimalities I could observe was that first, these agents are not flexible and adaptable to humans. Throughout the course of the training, self-agents develop very specialized preference, and they're extremely rigid about following these preferences. So, for example, in this one, the self-agent throughout the course of the training, it learns to, since the top pot is closer to the serving station, it learns to focus on the top pot more. And even like in this video, it was shown, I have to like describe it. So you can see that when the soup is cooking in the top pot, the human tries to start using the bottom pot because we have to serve as many soups as possible. But the AI agent refuses to participate or even use the bottom pot till the soup here is served. So they are, even though human is trying, but the AI agent is not ready to adapt to what the human agent is trying to do right now. So this is for this particular layout, and in this layout, the self-agent developed a preference to deliver the onions in a clockwise direction, and these were all clips from the user study. It would be nice if we could play them, but I'll just describe it to you. And even if the human tries to take the other route, the agent literally stands in the way and does not budge, and it will force the partner agent to follow its strategy, which shows it's not very flexible or adaptable. So, these kind of suboptimalities, flexibility, adaptability, or even like irrational preferences, it's not very natural to us. If we are playing this game, these kind of suboptimalities we wouldn't face as humans, even if we are learning, because in our user study, even the users didn't know about the game. They also had to learn the game as they were playing it. So these kind of suboptimalities are very different from how human suboptimalities are. And therefore, if we talk about using skill levels of AI agents for training self-play agents, then it doesn't capture all. Firstly, it presents the SP agent with suboptimalities, which is not similar to human suboptimalities, and it also doesn't capture possible human suboptimalities that the agent might face in playing this game. I also did a quantitative analysis where I analyzed the trajectories of the gameplay and basically judge them on the basis of these metrics, which basically shows how well they're able to coordinate. So, yeah, that concludes my work. For future work, of course, I still haven't been able to work on modeling human suboptimalities in a similar way, so more work is required to provide a more quantitative comparison between how AI learns to play and how humans learn to play. Thank you.
Questions?
Do you think your results would have changed if the domain or the environment you considered, or the game you considered was one where you had that's one where the players had to cooperate against another set of players rather than cooperate just to complete a set of tasks like the doing?
I think it will still be the same, because even if you are introducing other agents into gameplay, you still have to focus on how you're cooperating. So end of the day, the other agent will also be part of the environment in this game.
Any comment? Go ahead.
You mentioned that like there are issues of like when you in the original approach, like behavior cloning doesn't really capture the complexity of human behavior. Why?
Because the data set we are using to capture human behavior also doesn't necessarily capture all kinds of humans. Yeah, it basically comes down to how diverse humans can be, and it is like, in my personal opinion, it is pretty hard to capture one accurate human model. Rather, what would be a better approach is, when playing the game, maybe trying to use intent modeling to understand, okay, what are they trying to do right now, rather than have like one perfect human model, because that's not really practical.
Yeah. So I have a couple of comments on this. One, because it actually comes extremely close to things that we discussed in the class, so there is a couple of points to be made. One is, when she was talking in the beginning about, so this is a multi-agent thing. So Markov decision process for single agent against the nature. Okay. In a multi-agent game, you really need to model other agents, and you need to actually have the both models and so on. So the equivalent of MVPs for multi-agent scenarios is a Markov game. Okay. And if you do the Markov game and then go from there, then your RL is always just learning on top of some inference problem. So MVP, single agent RL, Markov game, multi-agent RL. Okay. The thing that's happening here is, what she's saying is, she says, for example, you have a second agent, obviously the world is not stationary because the other agent moves around. So she wants it to be stationary, which means you want to somehow assume that the other person doesn't have any intent, and they are just part of the process of the world. And it's extremely hard to make sense of that in general human scenarios, because the other agents actually have, as I pointed out, an inanimate world versus an animate agent are completely different. The animate agent might actually want to, oppose you or cooperate. So doing actual cooperation without having the models is pretty hard. And what the line of work is doing is, how far can you go without actually directly modeling the humans intent. So that's something that you want to understand. MARL, just as RL is MVP goes to RL, Markov games go to MARL. That's the real thing. Except you're not trying to solve MARL as if it is an MVP. That's basically what it's talking about. The other thing is the general, it's last but one talk, right? So the other thing is the general thing that in giving talks, one of the things that I found, and it's not actually about us, it's more of our failure, but one of the things I found is talks are showtime, unfortunately. So if all the things that you decide to show, if the video doesn't work, it could be painful, and so you should know. I think she did a pretty good job in trying to figure out how to deal with it and things that you have had before. But in general, if you're ever giving talks, in conferences, make sure that things are working beforehand. If you're giving long talks, make sure that everything works. It's nothing to do with the research, but if people can't hear you, It doesn't really matter. And the last thing I wanted to say is way in the beginning of the semester, I asked people to say one very interesting fact about yourselves. Hers is probably one of the most interesting facts that I've heard. I won't say it, I will let her say it if she wants to, but I just remember that. Thank you.
Yeah, so I basically, I am a trained classical dancer. Until I was in 10th grade, I was training to be a Kathak dancer. But then I read the brief history of time and then I got it so much into it that I decided to study science. So yeah, I was a pretty major switch and my parents were pretty confused, like why? I was like, oh, it's okay.
She mentioned that she was training in the school of one of the foremost exponents of Qatar, the guy called Bibli Maharaj.
Yeah.
So if you ever have to run 574's Got Talent, you would. Thank you.
Yeah. Thank you.
Lucas.
So is there anybody else left from the type 1 project? I'm just double checking. Okay, good. Thank you.
Path, right? Yeah. So did you give a PDF or PPT? Okay. Just give me
Language as an abstraction.
wait, I remember the previous. You did?
Yeah, I submitted it.
Okay. Okay, wait, let's see. I did see parts somewhere. Are you able to find it?
No.
No. Doesn't seem to be there though. Did you?
I put it there afterwards, yes.
Oh, okay. Okay. Good point. Wait. So do we have? Where is it? Is this the one? Okay. Just give me a second. Yeah.
My name is Parth and my topic is language as an abstraction for hierarchical deep reinforcement learning. So hierarchical reinforcement learning, it solves mostly long horizon tasks, trains hierarchy of policies. Performance is mostly depends on abstraction applied between these policies. But there are a few problems like with abstractions. When we hard code this abstraction, it lacks flexibility and task specific nature. And when we try deep learning to get this abstraction, it's mostly uninterpretable and hard to verify or change. So one possible solution is to define a high level policy that generates sub goals, and low level policy learns to reach those sub goals. Still, there are problems like goal states lacks the degree of flexibility required, and generalization to new problems is quite hard with these approaches. Language is very flexible representation. It's very easy to transfer ideas and communicate important things with language. And it's also compositional in nature, which is why it can be used to extract abstractions and knowledge transfer. But there is still problem with language. It has inherent ambiguity. Authors in this paper applied language as an interface between high-level policies and low-level policy. So high-level policy produces language instruction and low-level policy learns that instruction. There are a few benefits because of this. Low-level policy can be reused for different tasks. High-level actions are in language so that human can interpret this.
And rather than single goal state, there are set of goal states which our agent tries to solve. So to solve this, goal condition reinforcement learning is used, where MDP has been augmented with goal tuple, and reward function is also modified to augment goal with it. So policy is conditioned on goal, and objective is to find the policy for which discounted future reward is maximized. And Q learning is used to find optimal policy. To solve this task, environment was used, clever robot environment. It has data set, clever data set, standard data set for question answering, and Mujoku physics simulator was used to build this environment. There is also inherent generation module embedded in it, which creates language description and scene every time. This is the example of environment. Like there are objects and there is a description with a question which is not a current state, but we will take it as a goal state. And this is the representation used for learning, where O is the goal is fed with GRU, and tokens have been got out, and these are the objects which, so because in our environment, the objects are like 5 objects we used. So we have to get pairwise comparison between those objects to find the current state, because the description requires us to do so. So that's why we augment these options and then use goal to generate policy. High level policy has been trained with double DQN, where each time step it rolls out 5 steps of low level policy. And to this environment is sparse reward environment, because if the agent successfully reaches the goal with language, then only it gets reward. So it's quite hard to learn. That's why hindsight instruction relabeling algorithm was introduced, which uses K future strategy. So in it, if agent reaches the goal, then we will modify K states prior to that with a discounted reward, so that we can get reward signal. So agent will know that there is a reward in future following this trajectory. And in report, I have mentioned high level and low level policy algorithms, hindsight instruction relabeling algorithm, analysis of training, training with or without HIR algorithm, and also experiments with GPT-2 as a language supervisor for high level policy. Thank you. Questions?
So one question, did you implement the entire pipeline as they have presented, or was there a difference in the approach that you have?
No, so I found low level policy implementation and I used it to modify it differently.
Modified as
To apply high level policy, because they were sampling goals randomly from the environment, because environment gives a sample with instruction and scene. Okay, so they were just using it and training only low level policy. So I modified it to also consider high level policy, and then it calls with low level policy 5 steps that I as mentioned.
So, I mean, so what, I think what people have asked me, and I had a question, was did you re-implement or did you survey this paper?
Yeah, so I surveyed it and there was no full implementation of this paper. It was only partial. I used it and changed it for the experimentations.
But did you describe what experiments you did in
Yeah.
your report?
Yeah.
Okay, great. Any other questions? Okay. Thank you. Thank you. So that concludes the presentations and the semester. Any of you played with ChatGPT? Okay, so I checked whether ChatGPT can solve Sussman anomaly, and the thing is as usual. I mean, it's actually I picked it up, so you can check. Can you?
Yes.
So one of the things that you could, the good news is planning is still not solved. In fact, planning may never be solved by LLMs, as I have told you. Basically, it says, I think I was telling you guys this. I mean, the way the kids give plans, they sound very confident. I had this little kid who would tell me how to come to his house, and he'll say some gobbledygook and say, in the end, you say, then hang a quick left. And you just hear that hang a quick left, you think, yeah, the kid must have known the directions, like saying hang a quick left, that's the kind of things people will say. But actually the plan is completely nonsensical. Okay, so if you can show, okay, so yeah, go back. So here, that's actually the in colors, the Sussman anomaly problem. Okay, so you basically remember the Sussman anomaly problem, C, A, B, and then you want to put A, B, C. Okay, it's in the colors, and then go up here. Yeah. So yeah, and then that is the plan. Look at this. I mean, you don't know blocks word. It's good. I mean, there's so many steps. It's very serious. Totally nonsense.
When you get to stuff.
Totally nonsense. Okay. The thing that you have to understand is essentially, imagine it was not blocks word. This is the procedure for doing surgery. I'm one of the students in the class. That I just wanted to do the surgery. I asked this thing, and they'll give me the steps, and I just start doing the steps. I'll only find out after the lawsuits, etc. That the whole thing was wrong. It's like, because if I had known how to do it, then I won't ask ChatGPT. So I don't know. I think as people we pointed out earlier, the New York Times woman actually tried to make the Thanksgiving dishes by using GPT. ChatGPT is basically GPT on steroids. Okay, so that it's fun stuff. You can keep saying. So there used to be a time in Vision where it was told that you could go to any Vision talk, sit in the back, let the speaker drone on, and then stand up and say, "But what about noise?" And they'll say, none of the Vision algorithms will work with noise. And so now, for a while, at least for LLMs, when everybody's saying LLMs can do this and that, etc., you can stand in the back and then say, "But what about planning?" And I think you'll still be fine, in terms of that. So yeah, so I think as far as that is concerned, we are in good shape. One last thing, try to think about it. This is the very last evening. I mean, you guys are all losers because you're here, so you might as well think one more thing. So somebody actually asked me this question, and I was going to use it in the beginning to start the class off, but then we started late, so I didn't feel like doing this. So somebody asked the following very simple question. Suppose you're trying to test whether or not the GPT-3 these guys actually can solve problems. One idea that this guy had was he wants to give the same initial state and two separate goal states. Two separate goal specifications. So one might be saying on AB on BC, another thing might be saying on AB on BC on CK. Okay, and if you said that in that case, both goal states are the same. Do you understand what I'm saying? On AB, on BC, on C table is the same as on AB and on BC. In fact, Sussman anomaly, which if you remember, the problem with that is serializability, and you can't serialize the goal on AB and on BC. If you try to do on AB, then try to do on BC, then on AB will be gone. And if you do the other way around, it will again be gone. Whereas if you specified the goal state completely by saying on AB, on BC, on C table, it's serializable. In fact, every damn thing in this world is serializable if you describe the goal state completely. Okay, but on the other hand, describing the goal state completely is a waste of time. You want to just say what you want. I want you to say, you have to be here in the class, not exactly which shoes should be wearing, which color t-shirt should you be wearing, and so on. So the question this guy had is, he wanted to test out by giving multiple problems, all of which have the same initial state, different goal states, and in some cases, the goal states might actually be equivalent. And he would like to see if there is a simple way of checking whether two goal states are essentially equivalent, and how hard is it computationally. End of the life, end of the thing. So anybody has any idea as to what that is? It hard or easy? Worst case complexity. But so I'm just basically saying, you gave me a goal, okay, on A, B, on BC. Then I added to it on A, B, on BC, and then one more piece on CD, or one more piece on C table. Okay, on CD, that goal state is different from on A, B, on BC. But on A, B, on BC is the same as on A, B, on BC, on C table. Right? So can I, given two goal states, can you tell the same initial state, two goal states in terms of the specification of the goals, not the real state, okay? Can you tell whether they're equivalent? How hard is it to tell whether they're equivalent? That's what this kid's idea was, so that we can start doing it.
You just plan for each one, right? Or
how hard is it? I mean, is there a simple way?
Well, I mean, there might be some way for like this kind of domain, if you just made a fully specified state and work with them.
No, so that's actually a very smart idea, but that's a separate part of the thing. So why would I do? The question is, if I can give two goal states, can I tell whether they're equivalent? The answer is the only way you can. Suppose I gave on A, B, on BC, okay, and then on A, B, on BC, on C table. You are essentially asking, will every state where on A, B, and on BC are true entail on C table? Entailment from 471. Entailment is hard. In fact, you can only convert it into a planning problem. The only way you can actually solve this is it's not equivalent only. It's equivalent only if, instead of saying on A, B, on BC, on C table, if I said on A, B, on BC, not on C table, and then try to see if I can solve that planning problem. If I can't solve that planning problem, then it means that when on A, B, and on BC were true, on C must have been on table. Solving a planning problem is piece-based hard. So checking whether two goal states are equivalent is actually piece-based hard. So how would this kid go about doing the thing, which is sort of what Lucas is saying, which is start from a complete state. Imagine a complete state and just pick subsets of that complete state and give that as goal specifications. Then you would be fine. Okay, at least in that, that in some cases, at least that would be the case. Yes.
When you set the unspecified goal as the initial state, and you specify the goal state as the goal state, and then see how it extends.
That's a possibility too. That's also a possibility. But basically, the real question is, well, your point is that if the number of steps is 0, then yeah. But actually, the problem is that you have to look for the minimal plan. Because you can do all sorts of extra things by putting things down and up and etc. In fact, that's what this guy is doing. I mean, if you read this, this is exactly what that little kid told me as the directions, blah, 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 and then hang a quick left. And I hear the hang a quick left. Oh my God, this guy knows how to do mathematics. Maybe I should use his directions. This is all in English. It's actually very nicely written. How the heck are you supposed to know whether it's fact or fiction? In fact, this is a problem for all LLMs. In fact, I was just, this afternoon, I was talking for 1 hour to the Wall Street Journal reporter who's writing an article on, this stuff, ChatGPT. And one of the things that people don't understand, that was actually the other you can show me and then you learn. Okay, get it started. Which I want you, because I told her that that's like the most important thing to remember about the distinction, which is that LLMs, basically, any of these kind of systems, they're essentially trying to learn. Generating models are trying to learn the distribution of the objects. The distribution. Distribution of the objects basically might mean that you're learning the distribution of potential realities, not the reality in which you are living. Okay, so in fact, if you're following my Twitter last couple of days, I was wasting time on this. One was actually asking it about the AI history, and then it basically agreed that for Jürgen Schmidhuber was a kind of zilch, but then it said, thankfully he did get a Turing Award. Now you guys can laugh because you know who got and who did not get Turing Award. If some random kid somewhere who's like, that is clueless, basically thought, hey, why don't I ask LLM to figure out what's happening in AI? It says this with full confidence, just like that kid, and a quick left. Okay. And then let's assume that it's true. So the problem, that's the Jürgen should go back fully down and it basically say that it will say, despite these challenges, the contributions of the field have been widely recognized by his peers. He has received numerous awards and accolades for his work, including the Asian Turing Prize, considered the Nobel Prize of the Year. No, this is completely nicely written. There is nothing, you would think stupid people talk ungrammatically. This is how we have essentially evolved to confuse form with content. In fact, smart people can talk ungrammatically if they come from my part of the world and don't make sense of English, for example. Okay, they might be telling you the facts, but you think the farm is bad. These things get the farm extremely well. And it's very hard to be sure that the thing is thing. So this is the TLDR, the last part that I want to show you, that today's generative AI technology has mastered synthetic reality, funky images completions, but not the reality. There's only one reality, unless you're on something. You say there are multiple realities. So getting a picture which looks like a Hollywood star or a Bollywood star is much simpler than, can you generate me the picture of whatever, like Angelina Jolie. I won't give you the picture. You should just generate from scratch. Retrieving is the only way you can do it. You can't generate it because you're likely to. Okay, so because of that, actually, I think the planning parts for LLMs would be very badly, problematic. But you can use them for potentially heuristics, because they've been trained on enough. But it's been fun having you around, and I will get back to some of the presentations. I might get back to you for either clarifications or questions, and some of you we might invite you to come and present in my group if you want to, in which case there will be an actual drilling, because here I'm looking at the time there, we don't look at the time, we just until we're done there. Okay. But I think there are at least a couple of projects that were actually very nice. Thank you very much. Eat more food. Eat more food.
You like the papers?
Yeah.
Wow.
It's